name is Luiz Kruel, and I'm a technical artist for 5 years now. I started my career at EA Sports, doing shaders for Madden, NCAA, and other football titles. Then I moved on to Sony Online Entertainment and DC Universe Online, where I did a lot of shaders for that game as well as just general rigging and scripting and other TA jobs. And then now I am at CERN Affinity working on an unannounced project. So in this DVD, I'm going to show you guys how to write a full character shader from scratch. We're going to start with a very basic shader in CGFX and then build it all the way up to this character that has subsurface scattering, reflections, normal mapping, and all of the high-end current gen shader techniques. So like I mentioned, we're going to be using CGFX, which is very, very similar to HLSL. So a lot that you learn here, you'll be able to use if you had to do a HLSL shader. We'll also be using Maya, but you can pull this off in any software or even engine. I'm going to show you guys how to break down a shader and understand what makes a shader and all the different sections of it, as well as learn to start to modify it. And we'll be doing this sequentially, building from a very simple shader that has just a simple color. Followed by that, we'll be learning how to add lighting. So we'll be doing a basic lighting model, which will be our diffuse Lambert. Then we'll start learning how to add some ambient coefficients to it. After that, we'll learn how to do Fresneling, which will help with rim lighting. And finally, we'll learn how to do a full-on Phong shader, which, as you can see, we build each chapter on top of each other, and by the end of this lighting section, you'll be able to do a full-on Phong shader, which is pretty much industry standard to your most basic lighting shaders. After that, we'll start learning how to do textures. We'll start off with a basic diffuse texture. After that, we'll do a spec texture, finished by a normal map texture. Right after that, we will be doing UV manipulation. So we'll learn how to tile frequency as well as offset, as well as offsetting it by time. And then we'll learn how to do vortex deformation, which will allow you to do a lot of things from animating cars all the way to waving flags or cool looking dancing spheres. Then we'll touch a little bit on techniques. So we'll learn the difference between alpha testing and alpha blending, as well as how to do additive shaders. Then we'll do a pelletization chapter to where we'll learn how to have a shader that you can have a texture that drives different colors and texture blending across different parameters. And then we'll start doing our practic chapters where we'll learn how to do a nice car shader with some tricks on how to get reflections looking good, as well as the first chapter or the first shader that I showed you guys, which is our full-on character shader that has subsurface scattering, reflections, rim lighting, normal mapping, specular mapping, basically the works. So I hope you guys are excited about it. I'm looking forward to sharing all this information with you, and let's get to it. Hey everyone, so let's get started. I got a fresh scene in Maya 2012, and the first thing we need to do is make sure that our plugins are loaded. So let's go to Settings and Preferences, and then Plugin Manager, and just make sure your CGFX shader.mll is loaded. It comes with Maya, and this is what kind of controls the ability of creating a new shader node. And then after that, we can go into the Hypershade. And now you should have the ability to create a blend or a CGFX shader. There's also HLSL shader, which is really similar, and I'll go into those a little bit later. But for now, let's just stick with the CGFX shader. So go ahead and create one, and you'll see that it makes like a new shader node. So here in the attribute editor, you can control all the attributes, including the CGFX file, which is what we care right now. And what you need to do is you're going to load your custom CGFX shader into this field. So let's browse for a file, and I have it here ready in E3D Shader Production Shaders. And I have the super simple shader, which is the most basic shader we can write that just outputs a simple color. And let's go ahead and open that. So right now it outputs white, and you can see in the little thumbnail. But let's go ahead and create a sphere and apply our shader to it. Assign existing shaders, CGFX shader 1. So if you're in 5, you're not going to be able to see it. You need to go into 6, which is the textured mode. I think the other one is called shaded mode. Doesn't really matter. But then we can go back into the CGFX shader. And here's a little trick if you want to hide the wireframe. The wireframe is happening because you selected the sphere as opposed to the shader. So if you go ahead and select the shader, now the wireframe goes away and you have full control of the shader. So this means everything loaded fine and we have full control of the shader. So next I'm going to show you guys how to actually edit that file and kind of go deeper into what makes a CGFX shader tick. Alright, now that you guys are set up in Maya and you got your pretty CGFX shader loaded, let's crack it open and see what's inside. So for editing shaders, I usually use Notepad++. It's a free program you can get online. I like it because it does the syntax highlighting, which all it does, it puts pretty colors and helps you differentiate from what's actual code and what's comments. If you want to, you can use Notepad++ or just regular Notepad, but it gets kind of murky. So let's break this down. Usually at the top of the shader, there's a boiler head or a boilerplate. And this is where you say this is what the shader is, this is what it does, and notes for future people that are going to be editing the shader. And then at the very next area, and these can be arranged however the hell you want. They're just standard to be doing it this way. And that's how I've seen it done. But a lot of people break it down into multiple files and break the vertex shader out from the pixel shader. There's different ways. This is the simplest way that I know how to. So the matrices is kind of the magical part of the program, and you don't really want to worry about them too much. Just know that they're there and know that you might use them from every now and again. They're basically magical numbers that take a position and put it into object space or world space or screen space, and all that does, it's like, say if you have 100, you know that that's in relation to the world, or if it's in relation to an object or in the screen. That's all it does. And it's really useful for things like normal maps where you want to take a texture and then actually distort the object with it, but you really don't need to worry that much about them. Just know that they exist and you need them. And then after that, we have this description, which is a Maya thing. And it's only a CGFX shader thing. The HLSL shader doesn't have this, but it's just a nice little area that you can edit and put a quick description. So let's edit this and reload over here, and there you go. It's just to, again, to leave notes behind and help the user know what kind of shader this is. After that, we get into the parameters, and the parameters is anything that you want the artist to touch and to be controlled. You can hard code all these values, but then they're kind of useless. So ideally, we can expose a lot of these values out and let the artist kind of pick the colors they want. So this shader only has one parameter, which is the shader color, which is this guy. And this is the syntax to create one. Let's go through it and break it down. So float 3 means it's a floating precision number that has 3 components. And the floating precision number threw me off for a long time. That basically means it's a number that can have decimal points. Integers are whole numbers, and floating precisions are things you can have 1.1, so it's not just 0 or 1 or 1, 2, 3, 4. And then shader color is going to be the name of a variable that you're going to call in code later on. diffuse is what they call the semantic of the variable, and the diffuse is a special word that Maya knows to use a color wheel to describe the UI element for this. So just know that it's there. Later down here there's position, and then here there's color. It's just specific words that the compiler looks for. Then you got this little area, and this area basically allows you to add custom information on the variable. Most of this is for UI, and if in textures there's a little bit more shenanigans going on, but for now just know that this is just the name of this variable. That's where this comes from. And then this guy is your default. So since it's a float 3, there's going to be 3 numbers here, and since it's a color, it's going to be the red, green, and blue channels. So 1, 1, 1, it's going to be white. If you wanted to do red, it's 1, 0, 0. So just know that. And then the structs are another area that you don't really need to worry too much about. Basically, it's little bundles of variables that get sent from Maya or the game engine into the vertex shader, and then from the vertex shader into the pixel shader. And the pixel shader is also called fragment shader, and so that's why you'll see like V2F or A2P, and that's kind of generally how they're written. And here's where your normals are going to get sent through. If you have multiple UV sets, vertex colors, that's where it kind of gets defined. And then we have the main stars of the show. We got the vertex shader and the pixel shader. The vertex shader is very limited, and it runs once per vertice, and then the pixel shader is once per pixel. So generally speaking, you're going to have more pixels on the screen than you're going to have vertices, unless it's really far away, and then we can talk about that at a later point. But mainly the vertex shaders, mainly what it controls is position and preps everything up for the pixel shader. And some people can do skinning here, they can do cloth simulation, they can do just general vertex animation. But for now, we're just taking the position and then multiplying by a matrix to put it in the screen space, and then shooting across to the pixel shader. And then the pixel shader is also dirt simple. This variable before the function, so this is the function name. So the function name is pshader and vshader. And then this variable before it is what it returns, essentially. So it basically says, this guy comes in my function, and then stuff happens in the middle, and then this is what to expect coming out. And this V2F is a struct, so all that's going to come out of it is a position. So that's where all that works. But for the pixel shader, what comes out is a color, a float 4 color. So float 4 means that it has a R, G, and B, and it also has an alpha channel for the transparency. So all we do in the pixel shader is set that color to be our shader color, and then 1 for our alpha, and then we return it, which means spit it out. And if we wanted to change that to be red, like we just did, so we change it to 1, 0, 0, and save, and then reload it, and then you'll see that now your shader is red and it's hard-coded, and this doesn't work anymore because it's not hooked up. But congratulations, you just edited your first shader. And see, it's not that scary. So let's undo what I did, reload it, bam, we're back. And then last but not least, there's the techniques. The techniques are basically instructions for the shader on how to behave. And this is where we'll define things like double-sidedness or alpha blend, or if the shader is additive, or what kind of transparency it has. If it has multiple passes, which is things that's starting to be more supported in game engines. But for now, just know that all this does is this is what ties everything together. The opaque technique you're going to see here. If we added another one, you could pick it here. And all it does, it says, okay, I want to use the vshader function, which is this guy, as my vertex shader, and the pshader as my pixel shader. Don't worry about the other stuff. Doesn't matter for our purposes. So that's really all there is to it. Now you know how a shader is set up, and we can start mucking with it a little bit more and start getting more complex. Alright, now that you know the basics of how the shaders work, let's get into something a little deeper. Our first shader is going to be the base Lambert, which is kind of just diffuse lighting. And this will teach you about normals, it'll teach you about lights, and you will learn about dot products, you'll learn about the saturate function. So it's a lot of stuff for your basic simple Lambert shading, but you'll get you very, very far. Alright, so first off, we're going to open up the base.cgfx, which is very similar to the super simple CGFX, but it has a lot of the comments cleaned up, so it's a lot less. There's 80 lines in the whole thing. So the main differences between this and the super simple is the matrices here. I had a few more that we're going to need, and some of these we're going to need even further down the line, but just add them here and not worry about them ever again. And then the other part that is different is I've broken out the out color as a separate variable, so we can pipe in RGB and then pipe in the shader color and then the alpha 1, and then we do return out color. It's essentially the same thing as over here, but I'm just separating these out to kind of make them a little bit cleaner and easier for you to see. Okay, so the first thing we want to do is we want to pass the normal information into the shader, and to do that we need to go back up into our structs, and basically we need to add normal into the A2V struct and then the normal into the V2F struct. And all that means is the application, which is Maya, is going to be using that variable to shove the normal information in there, and then in the vertex shader we're going to do some math, and then we're going to output it into the pixel shader. Okay, so for the Lambert shader, let me just create a plain Maya Lambert shader so you guys know what to expect. So I'm duplicating the sphere. I'm going to create a directional light. Move it over here. And then I'm going to assign the basic Lambert 1 to the sphere. And then I'm going to switch to 7 so lighting is actually respected. So as you can see, the Lambert just works with a directional light and it's just a diffuse color. And the way it works is you have the direction of the light and then you have the direction of the normals. And then basically the shader can figure out if the normals are facing towards the light, then it should be white. And if they're facing away or perpendicular, they should be dark. So it's very straightforward, but we're going to learn how to do that with CGFX right now. So that's what we expect to end up with on this guy. Okay, so I'm going to kill the Maya shader for now because we know what that should look like. And we're going to go back into the shader. So just beforehand, what we're going to need is now we're going to need to know where the normals are because right now the shader has no normal information. And we also need to somehow tie this light into the shader. So we're going to learn how to do that as well. And then we're going to be able to put them both together and get the desired result. Alright, so let's bring up our base shader again. And now what we need to do is we need to add the normal information into this struct. And we also need to add it to this struct. So what that's going to happen is Maya is going to shove the geometry information, the normal of the geometry, into this struct. And then we're going to do another matrix multiplication there. And then pass it down into the pixel shader. And then after that, we're just going to output it as a color just so we can see what that looks like. So the normal is going to just be the same as the position, same kind of style. So you do float 4, normal, and then you have the semantic normal. And don't worry too much about those semantics, kind of go with it. And then for shooting across from the vertex to the pixel, we actually want to float 3 because the alpha of a normal is kind of useless and we only need it on the vertex shader for matrix multiplications because the matrix are 4x4s and we're multiplying against the float 4. So just know that you don't need that alpha, but you need it for math purposes in the vertex shader. And I also like to call it world normal, or just a convention, because you can have geometry normal, world normal. For now, let's just go with world normal. And then the semantic is texture coordinate 0, and that's kind of the generic semantic that we can use. And we need to keep track of that number because we're going to be adding multiple things and we just need to make sure that they're not repeated. So just keep an eye out for that, but don't worry too much about the semantic part of it. So now we actually want to do the math in the vertex shader. So we can do out world normal equals, and this needs to be that variable because this is a v2f, so just that you're casting into this variable. And we want to do a multiplication of the world inverse transpose. Don't worry about what this means. I never had to really know too much about it. And then here's going to be a new thing to where the result of this is a float 4, but we only want 3 components of it because this is a float 3. So to do that, we just do XYZ, and RGB also is valid, but all this does, it says, because if we don't have that, it's going to complain and say, hey, this is a float 4, you're trying to shove it into a float 3, what are you trying to do? So if we do the XYZ, it kind of truncates it down. So that's all you really need. The vertex shader is done, and then all we have to do now is let's make a new variable for the world normal in the pixel shader. That's a float 3 equals in world normal, and then here's going to be another new thing, and one that you don't have to worry too much about. Just know that whenever you're passing data from the application into the pixel shader, usually it's a good idea to normalize the vector, and all that means is that if the scales are off, we know that the vector has a perfect length of 1. Don't worry too much about how it works. Just know that if stuff is looking kind of weird, usually means that you have to normalize it. If you want to go into the deep math of it, you can look it up. But since this is more for artists, I'm not too worried about it. Just know that if it looks kind of broken, it's because it's essentially you need to freeze the transforms of the vector. That's kind of the equivalent. So let's do that. And we do that to kind of data that comes from the program, so we know that it's kind of sanitized and kosher. So let's output the world normal and refresh and see what we did. Pray to God it worked. Oh, bam. All right, cool. So this is what your normals look like. And you can tell that it worked because you have green in the top, red in the front, and then blue on the side. And it kind of lines up with these guys, so that's always kind of a good check. And there you go. Since we don't have any normal maps, it's just flat, and it works. Congratulations. So now the next thing we got to do is we got to bring in a light. Okay, so now that we have our normals being shown, we want to add the light direction in there. So to do that, it's really simple. It's just like a shader color. We're just going to be adding another parameter to the shader. So let's hop over into our base shader, and it's going to be the first of many copy and pastes. I just change this to be light direction. And since we want a better widget than the color widget, let's change this to be direction. That's going to give us a little nicer widget. Change our names. Let's change the default because we want it to be a little bit cleaner. This is part of the normalization thing. As a vector, you want everything to be added. Like if you add R, G, and B, it equals 1. And that's what normalizing will do behind the scene. So 1, it's going to be just top down. So if we don't have anything hooked up to it, it should just look like a top down light. And then we actually want to bring this into, let's just output it, see what it looks like. Kind of interesting. Let's refresh here. And you'll see that since nothing is hooked up, it's just plain green. So let's go ahead and hook it up. Do that. Now you have a light direction variable. So you right click, and then you'll be able to pick from locators or anything that you have on your scene. Let's pick our light directional. It's going to be black, which is interesting, but if we move it around, you'll see that if this is facing towards X, it's red. It's facing up, it's green, and it's facing away, it's blue. So that's what we kind of would expect. It's the same as the normals, so it's just displaying a vector, which is not terribly useful, but it's kind of good for debugging to make sure everything works. So let's do what we came here to do, which is do a dot between that light direction and the world normal. But actually first, let's normalize that light direction because we don't know what it came from. Or actually you can see, like, if I start scaling this, it will start doing some weird stuff and like dimming it or not, and this is what normalizing will fix. It will just make sure whatever we do to the light, it's an even number. So let's create a new variable, and it's going to be a normalized light direction. Let's use that instead. So this should be our Lambert. Let's refresh. And there it goes. So one thing you might notice, it's backwards, and this is a mystery to me and to many of why Maya's widget is either the Maya widget is backwards or the data is coming in backwards. It's kind of a mystery, but it's kind of a known mystery and one that we have to work around for a long time. Maybe someone out there knows how to fix it. So the way to fix it in the shader is to put a negative in front of it. So that means that we're flipping whatever light direction is. So let's reload, and there he goes. So right, there you have it. You have your pretty Lambert. Now what we want to do is we want to actually the shader color. We unhooked it up. We want to bring it back. So let's move this into another new variable called Lambert. Want to move that into here, and actually we want our final color to be a Lambert multiplied by our shader color. So we'll get deeper into the multiplication, the adding, and everything, but you should know that diffuse lighting gets multiplied by the texture color and specular lighting gets added. And what that means is if the diffuse is dark, you want your texture to be dark. But if the specular is dark, you don't want your texture to be dark. You just want the specular to build on top of the color. So we'll figure that out later. Right now, let's just see what we have. And we have an error. So it's awesome. So this is the first of many. Ignore this part. Let me erase it. Oh, awesome. So this is the error we got. It says unexpected token at out color. What this usually means is that I forgot a semicolon somewhere, and there it goes. It basically, the shader compiled just kept going since I didn't add a semicolon. You'll do this a lot, and it's okay. We all do it. So let's refresh that. And now, there it goes. Now if we pick red, you got a red shader ball. Awesome. So now you know how to do a Lambert shader. And this is the most basic lighting model you can do. So after that, we're going to add an ambient color in there. Just to, so this is not too dark. Alright, so now that we have the Lambert, we want to add the ambient color. Just to kind of give a little bit more in the dark areas, so it doesn't go pure black. And to do that is fairly straightforward. We just got to add another parameter to the shader so the user can control that color, and then add that to the Lambert coefficient. So first off, we want to change this guy to point to your Lambert shader. If you change the name, this will get you if you don't remember. And then we'll come back to our Lambert. If you lost the syntax highlighting in Notepad++, you can go back to language, C, and pick C++. And that will get you back. So what we want to do is we want to copy this color, paste, and then just change it to ambient. And then we want the default to be darker because we just want a little bit. And I'll show you what happens when you have too much ambient. And then we want to copy that ambient color, come back down here, and you want to add there. But because the way math works, multiplication always happens first. So what we want to do is, since we want these two operations to happen first, we need to put parentheses around it, and it's just like basic algebra. So that should be all we need. So let's refresh our shader. And there you go. Now you have a little bit more kick. Let me change the color to be white so we can actually see a little bit more. And you can change this color around. If you go to white, you're just going to get fully ambient shader. And if you go to black, you're going to get back to what you had with the Lambert. And you can pick like a blue or some other color. And let me show you what happens if we don't have the saturate. Just so you guys understand why it's important. So basically, since this is -1, even if you add 1, you're still going to get 0. So you're never going to get a fully perfect ambient coefficient. This is really useful when you want to do subsurface scattering, because say you want to do red, or like a dark red. Now you kind of get that bleed. And that's how people do like a cheap subsurface scattering, is they basically just add that color before they saturate the vector. But for our purposes, we don't really want that. So let's bring that back. And let's bring that saturate back. Refresh, and there you go. So this is one of the simplest ways. There's multiple ways of doing ambient. But for our purposes, since this is an introduction class, let's just stick with this one because it looks fairly decent. Alright, so next we are going to learn about the Fresnel, or Fresnel depending on how you like to call it. And then that is basically the rim lighting, and it's the beginning of reflections. Okay, so the next thing we want to do here is we want to add a specular highlight. But before that, let's add a Fresnel, which is kind of a halfway step to teach you how to get the full specular highlight. So let's bring this shader back down a little bit, just so it's a little more diffuse and it's not blowing out. And what we want is, the Fresnel is basically a rim light around the whole shader. And what we'll need to do is we'll need to learn about the I vector, or the view vector. And that's basically a vector of what you're looking at. And we can dot it against the normal, just the way we did the light, and that will give us a Fresnel. And it's essentially if you had a flashlight on your camera, but then we can flip it, and that will be the rim lighting. So let's go through that right now. Alright, so the first thing we want to do is similar to how we added the normals. We want to add the I vector. So let's hop onto our shader, and we're going to calculate the I vector in the vertex shader because there's a lot of matrix multiplication, and the vertex shader is kind of better to do that since it happens less often, and the multiplications with the matrices can be expensive. So first, let's add here in the struct. And we're going to use text chord 1. And like I said before, you got 0, 1, you got to just make sure to increment that. And that is what is going to go from the vertex shader into the pixel shader. So we'll need a couple of things. The way we calculate the vertex shader, or the I vector, is we take the position of the object and the position of the camera, and then subtract the two, and that will give us a vector from one object pointing to the other object. So to do that, we'll need a world space position of our object. And that's going to be a matrix multiplication, the world matrix, and the in position. So this is different from this. This is the position in screen space, and this is the position in world space. And then we'll need the camera position. And this is the one thing that varies based on your shader language. It's usually packed inside one of the matrices, but for CGFX, it's in the view inverse that we're going to get. So we want to do it's basically packed in the alpha of the matrix. Get it out. And you shouldn't worry too much if this is kind of too deep. Just kind of copy and paste it. You don't really have to fully understand what's going on here. It helps, but if you don't feel daunted, because I didn't for the longest time. And we're gonna shoot it across. So we're gonna put it in the eye vector, which is this guy, and we will just subtract one from the other. World camera position minus world space position. And just for the sakes of it, over here we're gonna do the same normalization process. And let's output just the eye vector. So one thing that's cool about CGFX and any programming language is that you can override variables. So basically, because this is going to happen, and then right after, our color.rgb is going to be turned into the eye vector. So we can leave this for future. We can comment it out by doing 2 slashes. Oh, 2 slashes. Or we can just leave it running since we're not too worried about performance here in Maya. So let's refresh and see what we get. So it's kind of like the light, but you're using the camera as opposed to rotating the light around. So Z, Y, and X. So it's working how we want it to. So now the same way as the light, let's dot it with the normals. So we can do 3 Fresnel equals dot vector. And technically, this isn't a float 3, like the result of this math is a float, a regular float. But since we might want at a later point multiply this by a light color or something else, it's always good to just have a float 3. So let's do that. And then let's output that. Refresh. And there you have it. You basically have a flashlight, or sometimes it's called a work light. But what we want is actually we want the black part to be white and the white part to be black. So what we want to do here is we want to flip we want white to be black and black to be white. And to do that, we just do 1 minus our multiplication or a dot product, and you got a flip version. So there's your basic Fresnel. It's a little too wide for my taste. So the way to grow and shrink things in CGFX is with the power function. So first off, let's just saturate this thing so we know it's not doing anything weird. And then we can do power, and let's just do a value of 3 for now, just so you guys see what it is, but eventually you want this to be a Fresnel power variable. So that's going to bring it a lot tighter. So let's create that variable just so we can have a nice slider. Okay, so what we want to do is we want to create a new attribute. We want to call it Fresnel power. We don't really care for any special widgets. There's a different way to getting the slider. I'll show you. So Fresnel power. Since this is just a plain float, which means there's just one value. Just set this here. And the new thing is we want, same way that there's this UI name magical word, it's going to be a UI widget, which is a slider. Okay, so we also need to add a few more things to make sure the slide works. We need a minimum for the slider, which is going to be 0. We need a maximum. It's going to be 10. And we need a step. Actually, these should be floats. Sorry. So So let's try refreshing. And now we have that slider. You can see it growing and shrinking. That's just to kind of allow the user to pick whatever works best for their material. So let's go back and add the Fresnel on top of everything. And like I mentioned before, the specularity is always added on top of everything. So this is going to be first, and then the result of that will get added to the Fresnel. But we'll have the Fresnel added to it. So let's delete that little part. Reload. So now we have our glowy X-ray sphere. So one part that people obviously are going to complain is, I don't want it back there. I just want the rim to be facing the light. So to do that, you guys should know by now, is you actually want to multiply the Lambert by the Fresnel. And that's basically going to mask the Fresnel a bit. So there you have it. Got a nice little rim lighting. And all we need now is the specular to have the full lighting model. Okay, so now the last thing we need to do before we get into texturing is a specular highlight. And there's many different ways of doing it. We're going to go with the Phong way. There's also blend and a couple of others. Phong is the one that it's fairly common. Blend is also very popular. But for our sakes, let's just go with Phong. And what we need to do is this is part of the math where you guys are going to have to kind of stick with me. We're going to need a reflection vector, which is, so basically we want a highlight here that's going to be influenced by the light and your camera. So you basically, as the camera moves around, you want that specularity to roll around, but as the light moves around, you're also going to want that specularity to roll around. So the way Phong did it is you create a reflection vector which is using it's the negative output of reflect the I vector, the world normal. And then what we want to do after this is we want to dot the reflection vector with the light direction. So this will give us the play between the three that we're looking for. So the other thing we want to do is we want to saturate this dot. And one thing that Phong is the Phong model is famous for is for the glossiness controls. So that works exactly the same way as the Fresnel works. So let's go ahead and add that power. And let's give it a pretty wet look for now. Let's give it a 30. But we'll do the same with the Fresnel power. We'll make it a variable later. Oops, did it on the wrong place. So let's give it 30. And let's just output just that to see what that looks like. Reload, and there you have it. You got your little sphere. The way Phong behaves, it kind of spreads as it gets towards the edge, which is nice. So you got your little highlight there. Let's go back and just add it to the whole thing. And while we're here, let's change that hard-coded 30 into a parameter. Print, copy, and paste to the rescue. Call it specular power. Some people call it glossiness. It's all the same. And let's crank this to be 100. And our default to be 30. So this is kind of like a math formula. You can look up what it's doing behind the back, or I might do an extra DVD where I kind of go deeper into the math. but for now it's just one of those that I have memorized or how it works, and blend is also the same, where it just, that's the formula. So there you have it. You can pick the specular power. So like the higher it goes, the tighter it's going to be, and the wider it goes. And then if you get 0, it does some weird math, so it explodes. So usually a good idea to not let the min be 0 too. So let's do that right now. So let's do min is 0.1. Now, really close to 1, but it doesn't let me go to, or for now, sorry. So now that will stop us. There you have it. Now what we can start doing is we can just start adding more attributes. So if we want to do a specular color, just duplicate that. Specular color. And we go here, and we can either do it up here, probably cleaner, or we can do it down here, doesn't matter. But reload, and if we pick this to be whatever color your heart desires, do a cooler or warmer highlight. Also, if you get darker, that kind of controls it too, or you can have a specular intensity float separate from it. So there you have it. Now you know everything there is to know about lighting models, or at least the very basic to get you all the way. And the next section, we're going to start looking at different shading, or not shading, texturing techniques. So we're going to add a texture map, we're going to add spec map, and we're going to add a normal map. Okay, so the next thing we want to try to do is set up a texture. And that's really straightforward. I'll show you guys how to do it. I also renamed the shader to Phong.cgfx, just so it's not Lambert CGFX anymore, just so we're iterating on there. And so let's go ahead and bring up our shader. And the way to do it, first thing, we need to pass the UVs, similar to how normal and position are passed from the mesh into the shader. We want to add the texture coordinates, which is what's called. It's another name for UV. So let's set it between position and normal. So, and then the UVs are float 2 because it's U and V. So we don't need a float 3 or float 4. You can keep it lean. If you have 2 UV sets, we can get into that a little bit later in the more advanced chapters. But you would do it a similar way. And what some people do is they'll have a float 4 in the pixel shader, and in the vertex shader they'll pack them both together. So you have the textures coming in, or the UVs coming in separate, and then they get combined in the vertex shader and shoot across on the pixel shader. That's just an optimization because each of these can get expensive on the consoles. So if we get too many of them, we want to start packing them together. But for now, let's just keep moving along. We have the texture coordinates that we just added, so now we got to add them down here as well. And I actually want it to be text coord 0 as the UVs because they're the more important one. So we gotta shift our numbers down. So let's save that, and then here, just like we did everything else, we do out text coord equals in text coord. And that's just because we're not doing anything fancy with the UVs. If we did scrolling or something on the vertex level, we can do it here. But we basically just wanted to move right along. And then now that we have the UVs, we actually want to add the texture as a parameter. So let's save. And then we come back up to our parameters area. And the syntax on this guy is a little bit differently. And I'll go with you guys on this. And one thing that you guys have to understand is there's the concept of a texture and the concept of a sampler. And they're separate. They're kind of like how Maya works, or I don't know if 3D Studio works this way, but Maya, you have the file node, and then you have another intermediate node before hitting the shader. And what basically that means is one node is just for the file, and then the other node is to how to translate that file. So there's a couple of settings that we'll learn that go on in that sampler state, and then that gets hooked up into the shader. So basically, the texture is just the file. The sampler combines the UVs and the texture into what we actually want to output into the shader. So enough talking. Let's get to it. So instead of a float 3, it's actually a texture. Let's call it diffuse texture. And then we go into our properties. Here, string name equals, this is just the default. You can just do something, doesn't really matter. Default color, DDS. It's not going to be that. Some people put white. That's just going to, for us, it doesn't really matter, but just have something in there. Becomes useful in actual production. And then UI name, just like the other ones. Texture. Can't type today. And then the other one is texture type. And this is to be able to differentiate between a 2D texture, which is like a regular texture, and a cube map. And let's add semicolons to all of these, otherwise we won't compile. So now we got the texture set up, and now we want the sampler. And you guys will understand what this is real soon. Diffuse map sampler 2D is just what type it is. So like texture or float 3. Diffuse map is what we're going to use to call it. And then this guy is just kind of roll with the syntax. These are the properties. This guy's a little bit different than everything else because he's special. So we want to point the texture, and the texture is going to be the diffuse texture, which is this guy. And then address U equals wrap, and address V equals wrap. So let me go through this again. Syntax is a little bit different because since we use these guys inside, we can't use them here. So we use the curly brackets. Texture is just pointing, this is the texture that's going to be used in the sampler. So when we call it, it knows how it's hooked up. And then this address U and address V, it's how the texture behaves at the border. So you can do clamp, which will basically pick the last pixel and stretch it. Or you can do wrap, and I think you can also do mirror. But for our purposes, just wrap. But if sometimes you might know in Unreal, you can kind of pick the wrap, like clamp U, clamp V. This is what's happening under the hood. All right, cool. So now we have this. Everything is set up on this side, so we can go all the way down to our pixel shader, and let's set this up. So we want to call this, let's call it, so we want to, it's actually going to be a float 4 because it has an alpha channel, and let's call it color map, just so it's a separate name. And then to call it just how there's normalize, reflect, bow, saturate, the new thing we're going to learn is text 2D. And text 2D is how you actually call the sampler. It's a function that takes 2 parameters, kind of like reflect takes 2 parameters and dot takes 2 parameters. It takes a sampler, which is going to be our diffuse map, and the texture coordinates, which is going to be in text coord. In a later chapter, I'm going to show you guys how to start manipulating this texture coordinates. But just to be brief, if you want to scale the UVs, you multiply a number. And if you want to offset it, you add. In the later chapter, I'm going to go through it with it a little bit more. But for now, let's just kind of keep rolling along. Let's just see if this works. So let's override out color and do RGB. And then reload. We wrote a lot of code, so take a minute to kind of look it over. So just to go back, I added the diffuse texture up here, the sampler diffuse map, we pass the UVs all the way across. And then we also pass the UVs through the vertex shader into the pixel shader. And we call the texture map using the text2d function. There's text3d and there's textcube, which we'll learn in the future. Text3d is not very used, but basically in some consoles you can have an array of textures, and you can basically pick. It's usually used for fonts and stuff like that, but don't worry about it. So we got our color map, we're outputting it here. Let's see what we got. So it failed. Why did it fail? So line 75. So it probably means that I forgot to put a semicolon somewhere. Line 75, and sure enough, boom. This will happen to you guys a lot too. So let's clear this outliner. See why we screwed up this time. Didn't like that guy. Why not? Alright, so here's what we did wrong. Sampler state, not sample state. So now we're seeing white because our texture currently doesn't exist. But we should have a diffuse map that we can, just like regular Maya, you're gonna get this little pop-up. You pick file, this guy, and then I have some CGFX textures. So there we go. It reads. We got our UVs. Everything works. It's beautiful. So let me close this guy out. So now that we have our texture, it's unlit because we are just outputting straight up the color. So now what we want to do is we want to combine these guys. So the shader color times color map. And we can break this down a little bit. This is your diffuse lighting again, Lambert and ambient color. This is your texture color, essentially, which is that shader color, which used to be your plain texture color, which we'll leave them there just if we want to tint the texture. And now your new texture, and then your speculars. So if you want it to, just for visual sakes, it doesn't make a difference, but you can kind of see this is diffuse lighting, this is texturing, and this is specularity. So let's reload. And there we have it. But as you can tell, it's nice, but we're missing our normal map and we're missing our spec map. So those are the two things we're going to do next. Alright, so the easiest one we can do now is the specular texture, because it's going to work very similarly, and you guys can probably figure out already how it's going to work. We're going to read exactly the same way, and then we're going to multiply it against that little chunk of code that's our specular lighting. So let's just do some copy and pasting. Call it spec texture, specular, spec here, and then make sure that these guys are connected. Otherwise, you're going to be reading your other texture. And everything, only thing we need to do now is we got to read it here. Load for spec map. Actually, let's name it something else just so it's not confusing. Let's spell it out here. Now we want to read texture coordinates. So, like we did with the other one, just check it out. Make sure everything went okay. That was really quick. Let's kind of slow it down. So we copied and pasted the diffuse texture into spec texture and spec map. Change some stuff around so it points at spec and it says specular as opposed to diffuse. And then down here we read it, and that's what it's called, a texture call. So we want to have as little text2d as we possibly can, because these are very expensive. Word on the street, as I've been told, it's that one of these counts for 32 instructions on average. So if you can figure out a way to do something with about 30 instructions, you're better off than doing a texture call. But and then we can talk about a little bit. So the way Unreal does or how we get the draw calls, and not the draw calls, the instruction counts, is through the compiler, and it's a little tricky. We can get deeper into it, but Unreal has it built in, and it's really nice. But for CGFX, you start learning how many instructions you kind of have just by the size of it. But usually you're gonna need like an SDK with a compiler. I don't think with just Maya you can get that information out. But anyways, stop rambling. Let's check out. So same thing happened. So we have a spec map. And then let's open the spec. Great. That's just a normal map that I took, and I added all the colors together. So it's not a perfect spec map, but it'll do. So now that we have our specular map, we can multiply it. So let's do it over here. So we're doing specular color over here times specular map. And so here's another thing that different people like to do this different ways. So let's see what this looks first. I'll finish that thought. So now the spec, you can see it's broken up, but the rim is still not. So depending on your taste or what your material is going to be, you're going to have to move that guy down. So you're going to move that guy down here. And you can break these out into variables too. So so you guys see how it's done. You can just pull this stuff out. And that was a float 3. So we can do float 3. We can do total spec or something. Or you can do final spec. That just kind of makes this a little bit cleaner. So now what that meant was that the rim is also going to get multiplied by the spec color. So it looks a little more natural. Then the other thing some people do, they like to pack the channels together, which what that means is the red channel means something, the blue channel means something else, the green channel means something else. So if we wanted to do it, we could do specular map.r for multiplying. So let's figure that out. So if you wanted to do the Fresnel gets masked by the red channel, and the specular color gets masked by the green channel, simply do that. So that's green. Make sure we have our parentheses in a row. So we got that guy, and we're missing one here. So what this means is the red map, or the red channel of that specular map, is going to be against the Fresnel, and the green channel is going to be against the specular. The spec map is usually a place where people don't want to put too much color. Some people like it, but a lot of people just want it to be a flat color. So they rather use that extra channels to do something else. Reflection is another place that the spec map goes. Usually it's specular intensity and then the gloss, which is the specular power. Which some people, instead of doing Fresnel power, they pick a map. Or some people do Fresnel, some people do subsurface scattering. It's kind of up to you. That code. See what this guy's complaining about. Okay, so I had another typo over here, and let's fix that before we go forward. And basically, Maya kind of rolled with it, and I didn't catch it, but the fuse texture and the fuse texture here. So now it's happy. Map it, and we're back. All right, sweet. So A little bit of amateur hour going on, but usually how these goes. Correct the specular a little bit and roll it out so we can see exactly what's going on. Pull the Fresnel power back. Now it's starting to look like something. Into my ambient color. So as you get a texture in there, things start to change, and you need to start moving some dials around. But that's starting to look cool. And even though we don't have a normal map, you're starting to get a lot more shape in there, and starting to look a lot better. So the next chapter, and will be the final chapter of this kind of sequential series, it's going to be the normal map. And that one has a little more tricky math, but it's essentially the same thing. And then after that, I'm going to break out and we're going to do more practical examples. So I'm going to bring in an asset, or I'm going to show you different tricks of the trade on how to do subsurface scattering, different not ambient occlusion, but ambient lighting. We're going to do cube maps. We're going to do a lot of cool stuff. So, but it's looking pretty good so far, and not bad for your first shader. So, see you in a little bit. Okay, so the last thing we want to do is the normal mapping part of it. We got our diffuse map, we got our specular maps, we have everything else in the lighting model hooked up and ready to go. The only thing missing really is the normal maps. Then we're going to start going into more advanced stuff like subsurface scattering, cube maps. I'm going to show you some tricks on how to make brush metal look without needing to blur your cube maps. There's a couple of tricks you can use that I've used in a few games before. But for now, let's get the normal map going. So it's really similar to the way the other maps work on the parameter side, but we also wanted to distort the normals. So the way the normals work is similar how you have this little guy here. You have normal, each vert has that same configuration to where you have the normal shooting up, and then you have the bitangents, or the binormals, and the tangents shooting on the other two directions. And that basically tells the shader how the lighting should work on it. And to distort it, and which by distorting I mean you're changing the way your normal information reads. So you guys remember before I was showing you how the normals are set up? You basically have X, Y, and Z directions. If we basically, the way the normal maps work is they distort those normals. So we basically have the normal map push the normals in 3 directions. So it can push it out, it can distort it up, or left and right. And what's doing that is you have the normals are shooting out, you have the tangent shooting one way, and then the binormal shooting another way. And that's kind of just how it's set up. The binormal and the tangents correspond to your U and V. So if you have a seam in your normal map, is because you usually have a seam in your UVs. It's kind of self-explanatory because it's a normal map and it's going to be using UVs, but it kind of throws some wrenches at a couple of things. But let's get started. So basically what we need to do to get a normal map working is we want to pass the binormal and tangent information through Maya into the vertex shader and then through the pixel shader, and then we're going to use our normal map to warp those 3 things and then put them back together to form our final normals. So it's a little tricky, it's a lot to kind of digest. There's a lot of secret kung fu going on here. You don't really have to worry about it. I didn't learn about it through about 3 years into my career. After writing a ton of shaders, I kind of just copy and pasted and understood that this chunk of code is normal mapping. But if you want to go deeper into it, I think I'm going to do a separate chapter to where I'm going to break it down a little bit more and show how everything works. But for now, let's kind of get started. So the first thing we want to do is we want to add a slot for our normal texture. So the same way we did the other 2 textures, copy and paste, rename from spec to normal. So there's all that's to it. The other part is we want to pass in the binormal and the tangent information. So we want binormal tangent. And there's also a trick optimization that you can calculate a third from these two by using a cross product. And what a cross product is, if you give it two vectors like that, it will figure out the parallel vector for those three, for the other two, which is, so if you have y and z, it can calculate x. If you have z and x, it can calculate y, and the other way around. So but for now, let's not even worry about that part. Let's just shoot it straight across. Some people will debate whether that's a good optimization or not, because you're saving a slot that's going through the pipes, but you're adding some more instructions in your vertex shader. So depending on your shader, you might or might not want to do it. But we're getting ahead of ourselves. So let's go back to Earth. So just like we did a matrix multiply on the normal, we want to do it to the binormal and the tangent. But got even more ahead of myself. So we need to, since we added them to the vertex shader going in, we need to add them to the vertex shader going out. So we actually have that world binormal that I started typing up. So we're going to add world binormal and world tangent. And then you got to renumber these. Doesn't really matter what numbers each of these have. It's not like these guys that they need to be perfectly assigned, because these are just generic slots that you can feed your data in. So back in here, we want to change that guy to be world binormal, and then this guy to be world tangent. And these are just matrix multiplications to get everything ready to be put in the right space. So now that we have those three guys set up, we want to come back into our pixel shader. And this variable is our normal variable. So we want to overwrite this guy so everything falls into place and we don't have to deal with it. So what we want to do is we want to read our normal map in here. So we want to read normal map. And if you remember when I was showing you guys about the normal maps first, or the normals, there's basically, you have 1, 0, and -1. So that's the range. So you can have it facing towards me, facing perpendicular to me, or facing away from me. And since the normal map only has values from 0 to 1, we actually want it to go from -1 to 1. So the way to do that is you multiply by 2. So now 0 is still 0, but we uncompress the range out. So it goes from 0 to 2. And then we want to shift the whole thing back down by taking 1 out. So now 0 is -1 and 2 is 1. So now we have a range from -1 to 2 to 1. So now that that is uncompressed, we want to override the same variable with the actual distortion part of our program. So the way to distort the normals is we're going to have three guys going on here. We're going to distort the X, or the tangents, with the red channel, the binormals with the green channel, and the normals with the blue channel of your normal map. And then we're going to add them all back together to give our final normal map. Normal map geometry, or normals. So to do that, we can do X, which is the normal, multiplies in world tangent. Then we can actually copy and paste it if we're feeling lazy. We do Y is going to distort the world binormal, and Z is going to distort the world normal. And as you remember, we should normalize everything that comes in from Maya, because we don't know what state it's going to be coming. Some engines do the normalization for you, but Maya doesn't, so just to be safe, we'll normalize it. So if you ever authored a normal map, you can kind of know that X and Y or the red channel and the green channel, are the ones that are doing the most work. Some people even compress out the blue channel because the depth, you don't really get that much out of it. You really get from adding detail on the X and Y of the normal. So basically you're adding bump around the edges so you can kind of get a roll up and down, but the depth is really reserved for other kind of parallax mapping and other stuff. But some people like it. Some people think they get good results. Some people compress them out. It's a lot of the shader stuff is kind of personal preference and how you like the thing to look. So let's reload our shader. So something happened, and that means that our normals got whacked, which is good. And now we have to hook up our normal map. So rock normals, and there we have it. So super simple. Got some awesome normal mapping going on. You got that fake detail. And just for fun, let's just output the normals just to see what it looks like. So if you remember how it looked like smooth before, that's what it looks like now. And that's what that map is doing. It's basically taking the red channel, the green channel, and kind of pushing and pulling it a little bit to get the effect that we want. So congratulations, now you have a pretty good production ready shader that you can use. In the following chapters, I'm going to show you guys how to do cube maps and a few cube map tricks, how to use ambient lighting for with cube maps, how to do brush metal looks and like blurry reflections with some shader tricks, and a lot more stuff. So it's going to be a lot of more practical uses. We're going to just put it in some models as opposed to just have some shader spheres and kind of play a little bit. So congratulations, if you made it this far. You have a full functional normal map Phong, which is a fairly substantial shader to be written. Hey everyone, in this chapter I'm going to show you guys how to do cube mapping or reflection mapping. And that's pretty much the ability for the shader to have a reflection map or a cube map, which is essentially a texture with has 6 textures, which is up, down, left, right, front, and back, and then map that properly so it looks like the material is reflective. So that's the simplest way to explain it. But let's get to it. So what we're going to try to do is we're going to add another texture to the shader, and this shader is a little modified. It's cubebase.cgfx, and what I did is I stripped out all of the texture information. So this is basically where we left off with the Phong that had a little bit of Fresnel in it before we started to the textures. And this is just so we can really showcase the reflection map, because once you start putting normal maps in there, you start to lose it. So I also added a torus in here just because they kind of look cool when they're reflective. And I made it a nice bright red Ferrari color. So once that's reflective, you can kind of see too a good use case for it. So let's get started and see this cubebase.cgfx. It's essentially the same shader that we've been working with, just doesn't have any of the texture information. So let's go ahead and add that. So you can copy and paste it from one of your other shaders, or you can just type it out. I'm going to type it out so everyone can see it. So texture, selection texture, open, close. Have the name for default. Can be anything really. Let's do default cube. Yes, this doesn't really apply to Maya as much, unfortunately, but it's always good to have it in there. UI name is reflection texture. And this is one of the changes. Instead of texture type for the cube maps, we actually want to do resource type. And the resource type is going to be cube. So if you remember from the other guys, this is called texture type, and you put 2D as opposed to 3D textures. But for this guy, we want it to be a resource type. And then remember we had the sampler 2D. Here we have a sampler cube, because that's going to be a different type of thing to read a cube map. Reflection map. And then the texture is going to be that reflection texture. And the clamp, since it's a sampler cube, the texture or the sampler has a little bit different parameters. So it has rep R to clamp to edge. And the way this works is because to read a cube map, you basically need a vector into the texture as opposed to just the U and V locations. So you need 3 components. And what that will mean is that we're going to want to use that reflection vector to read in as our UVs. And you can use the normal as well, and that we can see what that looks like. And that can be used if you want to use a cube map to do lighting. And to do things like spherical harmonics are essentially a blurry cube map. The way it's done, you can do it with the texture, or you can do it with some matrix math. I'm not going to get into SHs in this video, but something you might heard of, spherical harmonics. A lot of the kind of high-end games are turned to, or have been doing it for a while. And some people do it with cube maps. Some people do it with just random numbers. So let's do our actual sampling here. So, cube map is X cube. And then, so let's just output the cube map to see how far we've got. Go in here, refresh, and I screwed something up. What did I screw up? So it didn't like the state assignment. So as you do this, you're probably going to have a lot of errors, and it's kind of natural, don't worry. Let's try to figure out what we did wrong. So the fact that it's complaining about state assignment is probably something around here. Got those here. Okay, so here's a problem. It's not reps. It's rep. So let's refresh, and there we go. So it's going to be white because we don't have any textures here yet. And typos are ridiculously common when you're writing shaders, especially for me. I don't know, maybe you guys are better at it. But so let's use this Uffizi cube, which is from Florence. It's one of the free cube maps. So there you have it. You got your awesome reflection there. Perfectly metal surface is what we want to do. So you can see how it kind of looks cool on the torus. So now it's how do we tie that into a real shader? Or if you don't want just pure chrome, which would be cool if you're working on a Terminator game. But the way usually that's handled is you have that Fresnel term, you multiply the cube map by that. So let's go down here and let's do the Fresnel times cube. And let's delete that parentheses. And let's delete this temporary variable. And what that's going to give us is you're going to get more reflection at the edge than in the center, which is kind of what we want. So that's kind of starting to look good. But this looks really, really dead. And this is partially because of the way we did our Fresnel and we used the diffuse to mask it out. But that makes sense if we don't have any ambient term. But since we do, let's kind of add that to the mix. So here where we had the Lambert, also add your ambient color. Just like you're doing over here, do it over here in your Fresnel calculation. So now everything kind of got bumped up a little bit, but now you got this. It's more subtle because it's driven off this color, but at least it looks a little more natural. So, starting to look nice. So one of the things that we can do here is there's a cubemap trick that I'll show you guys. The one thing you have to notice is that this is a 4.0 shader thing. It's not really. You can do it in a shader 3.0, but for whatever reason, my CGFX doesn't like that function unless you're in 4.0. But what you can do is you can use a text cube LOD function to basically shift down the MIPS of the texture, which means you're going to get a smaller size of the texture, which in essence is going to give you a blurrier cube map. And the way that works, instead of a float 3, which is this reflection vector, it takes a float 4, which is the reflection vector, and then an extra number. Let's go give it 3, which is how off your LOD is. So 0 is going to be your highest LOD, and then 7 is the lowest, or it goes as far as you can generate them. So let's reload. You can kind of see that kind of got a little dumbed down. And this is really used for if you want to do brush metal or anything that takes a blurry cube map. For the perfect Ferrari look, it's not the greatest, but you can kind of see what it's doing. You can see that it looks a lot more pixelated. But once you have a normal map in there and starting warping things around, you can. I've used them many times. So let's undo that because we don't really want that. So there you go. You have that. Let's do one more thing before we go. Let's read in with the world normal as opposed with the reflection vector. See what that looks like. So basically now it's static, which is what you would expect. So this is used for sometimes you want to do lighting this way. And kind of aware that you want to do this, but just so you know the difference. It'll still work, but now basically it's just going to read it using the normals as the UV. That looks a lot better. You can still have full control of your shader. And now in these chapters, I'm going to start teaching you guys more of little tips and tricks as opposed to a more kind of structured lecture. It's more little one-off things here and there that will help you out. So I hope this is helpful and you guys enjoyed, and I hope you use lots of cube maps in your future. Hey everyone, in this chapter we're going to go through UV manipulation, and that is basically if you want to scale the UVs, which is if you want to tile this tighter or looser, or if you want to slide the UVs one way or another, or even we'll go through animating UVs to kind of see how I would go about that. So what I have open is just that Phong shader that we have, and I just assigned it to a plane so we can kind of see the UVs properly. It's a little bit easier to see if you had a sphere. And what we want to do is we are going to add a few parameters. So it's basically going to be a float 4, which means you're going to have 4 different channels. And 2 of those are going to control the scale of your UVs, and then 2 of the other ones are going to control your offsets, or translates and scales. So let's go ahead and get cracking. So first, let's go ahead and just add that float 4 and add it to the bottom. Your float 4, you call this UV scale translate, and what this means is that the first 2 numbers are going to be the scale Y and X, and then the last 2 are going to be the translate X and Y. Now we can take this diffuse out because we don't want it to be a color picker, and we want to change our default to be 1100. Yeah, 1100. What this means is that we want to by default scale the UVs by 1, so they're the same size, and we don't want any offsets. So one thing that we'll do is, you notice that everywhere that we do UV calls, like these three for the three textures, we call the in text word, which is the UVs coming in. We want to pull it out. I just call it UVs. And pull them out here, just so we can do math to it and not worry about having to do it in 3 different places. So what we did is we just created a new variable, which is going to be our modified UVs, and instead of having to do the UV manipulation in each of the texture reads, we just do it once up top. So all right, let's just make sure that we haven't messed anything up and that it will still compile. Okay, looks good. Still going. There it goes. And we have our UVs, but these don't do anything yet because they're not hooked up. So let's go ahead and do that. So for scaling, we want to multiply. And I'll draw you a picture to see what that will look like. So essentially, if you have, let me draw the picture in here. All right, so your UVs, if you think that, this is kind of like a graph chart. This is 0, this is 1, this is 1. If you multiply it by, say, 2, now this is 2, this is 2, and this is 1. So basically your texture that before used to take this whole thing, now is going to be tiled 4 times. Because this is 0 to 1, and then this is going to be 1 to 2. That's 1 to 2, 1 to 2. So basically, if your UV mapping is from 0 to 1, you get 1 texture. So logic would say that if you're going from 0 to 2, it's going to tile twice. Make sense? And if you wanted to scale it to 0.5, it will basically mean you're growing the UVs. Well, let's try it out. If we multiply it by, let's see what we call that again. UV scale translate. And the X and Y. And we'll reload. So let's multiply this by 2 and by 2. So you can see it basically, like I mentioned, it tiled twice. And if you do it 0.5, 0.5, now what used to go before this was 0 and 1, now this is 0.5. So basically you're just reading half the texture in the space that you used to read the whole texture. 2, 10, that might be too much. Yeah. But depending what you're going for and how big your space is, you might want to tile it to maybe 3. So the same way that when we had the scaling, so still think of this 0 to 1. Now if we add or subtract, basically we're going to be shifting things this way. If we add and then shifting things that way if we subtract. Because now instead of this being 0, this is going to be 0.1. So we'll be reading like this texture somewhere there. And then this is going to be 1.1. So it's basically, we're shifting everything over. So let's see what that looks like. And since we want the other 2 channels, it's going to be the Z and the W channel. One. So you see how it grew and it moved sideways? We can do like the shader. We can do it from here. kind of see, like as it grows, we're basically offsetting. And if you can see, this is how you would animate. If you want to see have scrolling UVs, you're basically going to keep adding to that number forever. And if you want to pulsate, you want to be doing some multiplication stuff. Hopefully that straightforward enough. If you want to scale, it's a multiply. If you want to offset, is a addition. Let's go ahead and try to figure out also a couple of parameters in the textures. So remember how there's this wrap? There's also clamp. So what wrap does is, as the texture goes out of bounds, like so you're going above 1 or below 0, it will just repeat itself. But what clamp does, it will pick the last pixel. Let me refresh. And basically stretch it all the way across. So, probably had this flipped. And you can see this is 0, 0, and you're basically, you scaled it down. So instead of tiling the 4 times, it just said, okay, I'm just going to take the last row of pixels and stretch it, smear it across, and take this one and smear it across. Sometimes you want to use this to advantage. Sometimes you don't. Usually you would kind of have a row of black pixels right at the edge of it, and then basically it would be black all the way through. And this is fairly rare to be used. You usually use it on effects, say like if you're scaling the effects and you're kind of offsetting it, or if you're panning it and you don't want it to mirror it or to keep repeating the texture on itself, you use the clamping. Or if you say you have a sprite that basically grows over time and you don't want it to, as it starts in the beginning, be tiled all the way across, you use clamp, and that kind of, the repeating goes away. But this brings also an important problem. If we did want to grow through the center, this kind of throws it off, right? Okay, so what we want to do to make it scale from the center is first we want to subtract 0.5 from the UVs, and then we want to add 0.5 at the end. Kind of basically shifting it to the center, and then we want to shift it back to the edge. Let's add some parentheses just to make sure that everything happens in the order we want. We want this to happen first, so the parentheses, so they're together. And then we want this whole thing to happen, and then that +5 we want it to be the very last thing. So there you go. Now you're scaling from the center. And let's do our little trick again. So that is really, really, really important. Sometimes especially when you're doing effects, that's when most of the UV manipulation stuff goes, is where you kind of want like a sprite to grow and explode. So there you go. So next thing we want to do is figure out how to actually scroll the UVs over time. So first, let's change all these clamps back to wraps. Just because we're going to be scrolling the UVs. And then, just like Maya recognizes the semantic diffuse, or say like normal or position, it also recognizes time. So if we do float time, it's time. That means that it knows to, whenever the shader is running, kind of shove Maya's internal clock into this time. So then basically all we have to do is we want to add time. Now let's also add a speed, because time is going to go really, really fast. So let's add a float 2, speed xy. Copy this. And let's make the default 0.5. So basically what we're going to be doing is there's going to be the offsets, and then we'll add another offset, which is going to be our time. And then time speed XY, just because time by itself can go pretty fast and we might want to control speed a little bit. So reload, and there you go. You can hit play and just watch it scroll, but since it's doing X and Y, that's why we kind of get that diagonal motion. If we took out one of them, that, speed it up, you can kind of see where this is going. You can do a lot of cool stuff. If you put this on a sphere, looks pretty neat. Here. Apply that shader. Oh. You can get some really cool water this way. Yeah. Imagine if this was a water kind of wavy texture and just dripping over as a fountain. Or this as anything, really. So now you know that if you want to grow the UVs or anything in general, like positions, we'll see in a little bit later, it's the same kind of deal. Basically, if you want something to be bigger or smaller, it's going to be a multiplication, and if you want to slide something sideways or in any direction, it's an offset. So hopefully that all makes sense. Hope you guys are enjoying it so far. I'm having a blast. And yeah, move on to the next chapter. Hey everyone, in this chapter we're going to look at vertex animations, and this is going to be just like a brief overview of everything you can do, and we're going to do a waving flag and a couple of other things in this chapter. So to start off with, I just have a plain red sphere. This is from where we left off on the Phong chapter, so we haven't gone into textures yet, but everything is there. I've made a new vertex anim CGFX just so you guys are in the same place that I am in the shader. And it basically just kind of like the base shader color, ambient color, and then the Fresnel and the specular. I can go through the shader a little bit with you guys. Bring it up. So you can go through. It's the same kind of setup we've had. And all we're gonna do today is we're gonna play in the vertex shader a little bit. We haven't done too much work besides just pushing information back and forth. And the main line we're concerned with is we want to try to modify what this out position is going to be. So at first we're going to just add some offsets and kind of see what we can do, and then we'll start getting into some fancier stuff. Alright, so the first thing we want to do is we want to open up our shader and just get familiar with what everything is going on. Pretty much that Phong shader that we left off with. It has no textures and just some basic, the full lighting model. But we don't really care about the pixel shader in this chapter. We care about the vertex shader. And the main thing we want to do is we want to change what this in position is. And we're going to do some animation on it. We're going to just do some offset, some scaling. In theory, or not in theory, in practice, you can do full scaling in the vertex shader, but that's way beyond this lessons. What we're going to do is we're going to do some basic manipulation. So to start off with, I want to make a new variable. That's going to be a float 4 because our position is a float 4, if you remember from here. And let's just call it deformed position. And that's going to be the in position. Then we override that. So basically, it's going to come in, and then from the in position, it's going to be transferred over to the form position, which is then going to be used in our multiplication. But in between, we're going to do some stuff to it. And one of the first things we want to do is, let's just set a parameter so we can control it. So let's do vert offset. Call this offset. Let's zero this out. If you guys seen the chapter on UV manipulation, you'll know that if you want to scale something, you want to do a multiply against it. And if you want to offset it, you want to do a plus or minus. So what we want to do for just to get our feet wet is we want to add to the XYZ of the deformed position. Actually, yeah. So what this means is, let's do XYZ, and then XYZ, because this is a float 3 and this is a float 4. So we don't want any problems. And what we're saying is that this guy, really now what he means is it's himself plus that offset. And what this should do is this should move him around. So refresh, and everything's good. So let's see, if we offset in Y, you can kind of see that Maya still thinks the wireframe is down here, but the shader is actually displacing it. So if we select it, you kind of get the wireframe to go away. So you can kind of see that the world is our oyster and we can do whatever we want now. The shaders, or the vertices, are under our control. And let's go into the channel box. Up. Select it. Yeah. So I've animated cars in games that don't have an animation system by just animating the offset, kind of like cars in the background. We made little cubes and put a car texture on it, and then we basically did this over time, which from the UV manipulation you should remember how to do it, but we'll cover it again. And yeah, it's a very powerful tool to have. So now we know how to offset it. So, but if we wanted to scale it, to kind of get a beating heart or a pulsating thing, we want to do a multiply. So let's just do that and see what that looks like. This is basically going to be doing the scale on the mesh. Reload, and that failed. Okay, so it went away because our scale is currently 0, 0, 0. So if we bring it back 1, 2, 1, 1, 1, since it's a multiply, you shouldn't have 0, 0, 0. So I want to select the vert or the shader, and there you go. Now if we select the material, well, yeah. So now you can see that this offset is really doing a scale. So if we do scale of 1 is the regular size, scale of 0.5 is half the size, scale of 2 is twice the size. So it seems trivial, but if you wanted to do something pulsating or like a jellyfish or a beating heart, you could definitely do it this way. But let's get into a little more interesting stuff with some time manipulation next. Alright, so now it's time to get fancy. So now we know that multiplication is going to do scaling on the mesh, and addition is going to offset it. We really want to kind of play with the scaling. And one thing that I'm kind of interested in is showing you guys how sine waves work. And if you kind of have some basic math, sine wave is just, it goes like a squiggly line. And it's basically really helpful for doing pulsating effects. So let's basically try to pulsate the sphere up and down. So to do that, we're going to have to add the time variable back in. So let's just float time. And the secret is to give it the semantic time, just like we had the semantic diffuse. And now that we have it, we can do, we want to multiply sine wave of time. And what this means is, as time goes, you're going to get a sine wave kind of bobbing up and down. And we want to multiply the whole thing by the vert offset. Since we wanted this to be clean, I'm going to put some parentheses around it. So let's see what this is going to give us. So if we play, you kind of see it it basically goes to 1, and then it goes to -1. And we don't necessarily want to go into -1. So we can do two things. We can saturate that sine wave. Which what that's going to do is it's going to sit on 0 for a long time while it's going to -1, and then as it comes back up, then it'll go through. So basically, if you remember the saturate from before, the saturate takes your range and squishes between 0 and 1. But since the time is kind of hanging out in -1 and kind of coming back all the way back up, the saturate is going to be squishing the whole thing up to 0. So you're going to have the time that it goes through 0 forward, it's going to be scaling, and then it's going to come back, and then as it goes through -1, it's going to get slammed in 0. So what we really want to do is we want to shift that whole sine wave up. And if you remember offsets, you're going to do an add. So what we want to do is we want to add, let's try to add a point. Set 1 to the whole sine wave. So now in theory it goes from 0 to 2. So if we want to go back to 0 to 1, we half it, which is multiply it by 0.5. So this might start getting kind of nasty. So I'll go a little bit slower. Make sure that we have enough parentheses here. So we got that parenthesis, that one, and we're missing one. So what is that? It goes to 0, and then it goes to 1. Let me break that down a little bit more. So the sine wave is essentially a curve that's going to bob up and down from 0 to 1 and then to -1. By adding 1, we basically shifted that whole curve up. So now instead of -1 to 1, it goes from 1 to 2. But then since we just want it to go from 0 to 1, we half it. So it goes from 0 to 1 as opposed to 1 to 2. From 0 to 2. So if we take the half out, now the largest the sphere will grow is at twice the size. Now what we want to do is, we're cool with the pulsating, but we want to try to get the beginnings of a waving flag. That's kind of like our goal. So instead of a scale, what we're going to do is we want to move it up and down. And to do that, as you might imagine, instead of multiplying, we want to add. So right now it's going to be moving in all three directions, so it's basically going to diagonal up. And since we do want it to go back down, we can kind of stop all that nonsense we added, kind of control it. So we really want, come back to basics, just want the sine wave and the vert offset. And that vert offset is basically going to control which direction and by how much that sine wave is going to mess up with the deformation. So now it's going to go from 1 and -1 in all three axes, which we just wanted to see going up and down. We zero everything out, and we just do y. So it goes down 1, then it goes up 1. If we wanted to go further, we can do 10. And since it's a sine wave, it has a nice kind of fluid motion, which is nice. So now we kind of know the basics. But to visualize the curve a little bit better, what I want to do really is put this on a cube. So let's create a cube. And kind of make it long. This is essentially going to be our flag. I'm growing it out on X. Let's assign the shader that we have. And right now it's going to be doing that up and down, which is great. Let's subdivide them a little bit to 5 everywhere. And basically what we want to do now is we want to throw that sine wave, as opposed to being the whole mesh, we want it to be based on the vert position on the mesh. And hang with me, and stuff is going to start getting clear very, very soon. So what we want to do is, just like we had that vert offset, kind of truncating everything down, we want the position, like the X position of the vert, to also be a factor. So what we want to do is we want to basically shift time by the position. And it will basically send a ripple down the mesh. So as you can see, now it's starting to do some funky stuff. And let's add some more subdivisions to this cube. So you can kind of tell that it goes up and down, up and down. And instead of being 10, let's just do 1. See what happens. Across the other parameters. Twice. So by now you guys are probably super confused. And hopefully what I'm about to do is going to clarify everything. So the way sine waves work is you basically have a frequency, which is how many of these bumps you got in throughout your curve, and then you got an amplitude, which is how far each of those points go. So right now we have the controls for the amplitude. So if you wanted to deform more, kind of put 10, and it goes really sharp. But we don't really have the control for the frequency besides the vert. So what I want to do is I want to add that, and that's going to start making things a lot clearer. So let's add a new parameter. It's just going to be a float. Let's call it animation frequency. And let's go from 0 to 10. We can bump this up later. And the frequency we want is 1. And you can watch some like physics videos online, and it goes into more details on the curves, but I just want to try to show this to you visually, the changes it's going to do. So we want to multiply the frequency by that position. Reload. So if we drop the frequency, you start getting lower curves. And if you up the frequency, you're going to start getting more. So 1 is going to have what we have, which, since it's kind of like perfectly in sync, you can't really tell the curve kind of moving forward. You just see the verts kind of popping up and down. So if we drop the frequency, you can kind of see what it's really doing. So that's really what a sine wave should look like. Hopefully that clarifies it. So now we have our sine wave, we have the frequency, and we have the amplitude. So this should be a lot more to what you guys are used to seeing as a sine wave. And sorry it kind of took us a little bit to get here, but I wanted to kind of step through everything. So there's our sine wave. It's going to go from, the offset is -3 at the lowest dip, and then 3 at the highest. We can make it be 1. So it basically bobs down to 1 and then -1. Or you can do 10, which gets really crazy. And you can kind of see our little sphere back here kind of hanging out like a dolphin. And you can kind of do some interesting stuff. So back to sine waves. We have the frequency, which is basically how fast it tiles, and as you get closer to 1, you're going to get that, and then as you get closer to half, you're gonna start, or closer to 0.1, you're gonna start getting more to where you can see what's going on. Let's do maybe not 5. Now it's starting to look kind of cool, and this is also very dependent on your mesh. So let's see, not that guy, that guy. Maybe not so much about the mesh. But yeah, if you start go lower, you start gonna get chunky, but after a point it gets pretty smooth. So up. Now we have the flag kind of going that way. Let's see if we can get it going that way as well. And that's where this the X, Y, and Z controls come in handy. And I just animated a tentacle in a shader doing this stuff, so kind of sky's the limit on this. And you can see it's doing both up and down. You can see the sphere's kind of freaking out a little bit, but you can kind of see how you can make a tentacle out of this guy. I basically just had a long geometry and it kind of did the swimmy. Swimmy motion. So there you have it. So that's basically vertex animation. So sorry if it got a little bit too confusing. Let me step through it once more, just so you guys are kind of clear on it. Let's open back up the shader. So we have the position comes in from the vert. We want to store it into a different variable just because we want to keep the alpha alone and we want to just mess with the XYZ and we want to kind of put the deformation in a single line. What's happening here is you have a sine wave. So if we just did the plain sine wave, you saw what that does. It kind of just bobs up and down. The plus is for an offset as opposed to being a scale. So we basically want the verts to shift. We want to shift time, and time is basically the variable of the sine, and we want it to be time because time is constantly changing. So your sine wave is constantly moving. And then we're offsetting that time by the position, which means it's kind of going through. So this position is 1, this position is 2, so it kind of offsets the sine wave a little bit more. And then the frequency is how many of these we got. And then the offset is the amplitude. And just for fun, let's set another variable, which is speed. Just so I can show you guys that how to control it. So these two guys get multiplied first and then offset time. But if you wanted speed, you can basically speed up time. So since multiplications happen first, animation speed is gonna speed up time or slow it down. So basically, instead of taking 1, 2, 3, it'll take faster or slower based on your speed variable. And then it's gonna get offset based on the position and the frequency. So if we come back here, stop this so we can refresh the shader. And now we have that animation speed at 1. Now we can do 10. It's gonna go a lot faster. 0.5, it's gonna go a lot slower. Hopefully it's helpful for you guys. Then so we have this on a flag somewhere. We've done it before, or you can do some crazy stuff if you have a different shape. And you can see the geometry is still in there, and as far as my concern, that's where the geometry is. But the shaders doing all the heavy lifting. So there's no joints in here. If you wanted to do this with joints, it would basically be a ton if you even would be able to. And the animation cost would be huge. So this is a really good usage of shaders that not that many people know about. I've done things like the cars animating that I mentioned before. I've done a Ferris wheel to where it was rotating the whole mesh with the vertex animation. I've done tentacles and water and moving flags and a lot of things with shaders. It's really, really powerful, and you get effects that basically you couldn't with verts, or you could do this with cloth, but the price, if you wanted to have like 15 flags, it's kind of wavy in the background. You kind of just want the noise there. You just want something moving. So, and hopefully you kind of get a little bit more understanding on how sine waves work. Hopefully it wasn't too confusing. I know it's a little bit of math, and math is hard, but frequency, and speed, and amplitude. Those are the physics names, and that's essentially a perfect sine wave. Cool. Hope you liked it. Hi everyone. In this chapter, we're going to take a look at techniques. And techniques are usually related to blend modes, which means something is opaque, transparent, alpha blended, alpha tested, backface cold, additive, and all those kind of fun things. So we're going to run through all of those, and hopefully you guys will have at least a good, solid, basic idea of at least how everything works and where in the shader they are. A lot of it is going to be dependent on your engine, or be it Maya, or be it Unreal. You might not have to mess with it that much, but if you have a custom game engine, it's definitely going to change, and it's going to change from CGFX to HLSL. So a lot of it you might need to look up online on like the proper syntax, because it's going to change. But hopefully this will give you a kind of basic idea of how everything works under the hood and where to start poking around and what things should be called. Okay, so what I have loaded here is a basic sphere model with a normal map, spec map, and diffuse map. And this is what we got from the texturing, all the way from the normal map. If you've done that, that's where I'll be left off. I've also made a new shader called techniques.cgfx, which is kind of the starting point for this chapter. So let's crank that guy open. So as you can see here is the regular, that shader that we've had for a long time now. And the part that we really care about in this chapter is this part. And like I said before, the technique, like the syntax works, is you have the technique and you have the technique name, which is going to show up here. And depending on your shader, this can be a drop down or just a list, which you'll see. The different passes, Maya doesn't really like multiple passes, and some engines, or I'd say most engines, are kind of iffy on that. They have to be specially compiled for that. And then you have the vertex shader and the pixel shader. But in between, in here, you can add some magical words that will make the shader behave differently. So first, let's just take a look at transparency. So on the beginning of the shader, I've made it so the alpha is the Fresnel term. So basically, the center of the shader is transparent and the edges are opaque. So as our first technique, what we'll want to do is we want to see what a transparent technique would look like. And there's two names for transparency. There's alpha blend and alpha test. Alpha blend is the full nice transparency. And some engines, including Maya, have a really hard time sorting with those, because basically you lose the depth information if you use those techniques. So there's the alpha test, which is also called 1-bit alpha, which means it's either transparent or it's not. And you can't have a nice transition. You just have, it's either alpha or not alpha. And in the alpha blend, you can kind of have different gradients of alpha. So let's start with alpha blend. technique, we have one pass, and here's where the magical words that will change per your engine, but for CGFX is alpha blend enable. And this one it's fairly common. So if this doesn't work in your engine, you can ask around or look in the internet, because if it's not this exact wording, it will be something extremely similar, and then alpha blend would surely be a part of it. So let's reload Maya, and now you'll see that we have the opaque technique and the alpha blend. So let's click alpha blend, and you'll see that Maya has also backface culling turned off by default. But if you kind of get around the sorting, you'll see that it is behaving the way we want it to. You have the nice fall off from transparent to opaque, but you have that beautiful sorting fail. And we'll want to address that. And the way we want to address that is by turning off or by turning on backface culling. So we don't want, what we're seeing here is the inside of the back faces. So like these guys, and we really don't want to see them. We kind of want it to behave this way. And sometimes you want back face culled, sometimes you want it front face culled, depending on your shader, but let's kind of go baby steps. So what we want to do is we want to do cull face enable equals true. And we'll also want to say that front face equals counterclockwise. And I'll show what this means. So there's clockwise or counterclockwise, and this essentially means it's front face culled or back face culled. So if we reload, you'll see that we're back face culling properly. If we wanted to go back and change that to be clockwise, you'll see that now we're looking at the inside. So basically, what that tells you is the winding order. So it says it's essentially front face or back faced. And you might want to do this. So the one usage that I can think off the top of my head is if you want to do, say, let me show you real quick, an outline shader. Usually you can do two passes of the same sphere, scaling this sphere. Whoop. Nice. Let's move this to 0. Now let's scale this to 1. And maybe a bit more. Then let's make sure this guy is all zeroed out. So sometimes people do outline shaders this way, to where they have two spheres, one inside of each other, and one is front face culled and the other one is back face culled. So you kind of get, like, if you wanted to do an outline, that's one way to do it. We've done things like this before. But let's delete that guy. This is kind of like an edge case. 99.999% of the times you're going to want back face culled. Yep. So let's go back here and do counterclockwise. And reload. And there we have it. So, and the other thing we can try to do, since it is the Fresnel that's getting controlled, we can change the power, and we can kind of see it kind of being dynamically controlled. You can use this to fade objects on and off, or you can have an alpha texture. Most likely, this is what you have. Or in edge cases, you might want to have the Fresnel be. And one thing you can kind of do too is you can invert the Fresnel. So we can do 1 minus. And what that will give us is just the front faces. So you can basically fade it as it goes off the edge, which can sometimes be desirable too. So let's go back and undo that. So, okay. So now we have our back face culled and transparent shader. Do that again. Got that guy going. Got it refreshed. And so now let's do the alpha test. So this is really expensive, and sometimes it doesn't sort that well. In most engines, this has to be done on a separate pass because it doesn't sort well. And it's kind of something engineers don't really want us doing all too much. If you have a deferred engine, which is like deferred lighting, it might not even be supported full transparent. So you kind of might be able to, or you kind of might want to test out the alpha testing techniques. And a lot of, you'll see what it looks like, and you'll realize that a lot of games use that instead of the full transparent. And the other thing to note too is backface calling saves your rendering time, and like basically cuts it in half if you can backface call. 90% of the time you're going to be backface calling without even noticing. But if you're explicitly writing the shaders, then there's just something to kind of keep in mind as a big optimization. So for alpha testing, we'll duplicate this to alpha test. And we change this to alpha test enable. And then for alpha test, basically, since there's a threshold in there that says after this point of alpha, it's on or off, as opposed to the nice gradient, there's an extra little parameter that we can add, which is alpha func, which is the function. And this one also will change based on your shader, so keep an eye out. Just know that there's somewhere in the shader that you're going to establish a value. Sometimes it's called a reference point of this is where in the alpha I want it to be the clip. And then you want to say I want it to be greater of equal, or less than. Basically mask out anything smaller than this number or greater than this number. So for Maya, you have to do a float 2, and you do greater. And for our sakes, let's do 0.3 as the kind of threshold of alpha. And let's go back in. Now we have our new alpha test. And you'll see how it looks a lot rougher than the nice alpha blended. And you will start noticing that a lot of games will do this, especially if you see like characters' hair will use this a lot. And it doesn't look as nice, but it runs better. And some games will even use this to kind of blend objects in and out. So you have it full opaque, and then as the LED kind of comes on, it kind of cranks that Fresnel until insanely high number, and then it'll just pop it off. One is just like a sliver. So let's go back to 1. So that's the difference between alpha blend and alpha test and opaque. And that's how you get to them here. And that's basically how to control them in a shader. Check out your local listings on this, because it's going to vary greatly based on your engine. But just kind of understand that there's that alpha function in every time you want to do an alpha test, regardless if it's CGFX or HLSL. And you're going to have somewhere that you're going to have to give a number to control the threshold, and you're going to have a greater equal, or something sounding like that inside of your shaders. And just so you know, kind of some people call full alpha and then one bit alpha, because it's kind of on or off. And the last one we want to do is the additive. So additive is really useful if you're doing X-ray and hologram kind of stuff, and it's kind of a neat trick. So let's kind of touch on that. And this one is even more kind of black magic. Instead of alpha func, it has a blend func, and it's set into. So basically, every blending mode will have where is it blending from or where is it blending to, and usually you have source alpha to inverse of source alpha. Let's see if this will even run. Nope. So this is where the language barrier comes into place. So if it's not inverse source alpha, sometimes it's 1 minus source alpha. If it likes that. No, it still doesn't like that. Let's see what else it could be called. Okay, so it's not blend Phong, it's blend Fonk. So inverse source alpha will work. So basically what this says is, basically transparent means anything that's the source alpha, which is going to be Fresnel. This is going to dictate what's transparent, and the inverse of this is going to dictate what is not transparent. So the way blending works is you have the alpha, and then you want to do the inverse of the alpha, and you basically add them two together. And that's essentially how alpha works. And I'm going to touch this on the pelletization, but for now, just kind of stick with me. In the next chapter, I'm going to go through how to blend textures together, and this is essentially what this additive stuff is doing. But for now, just kind of stick with us. Usually, you're going to have a value that's your alpha value, and then you're going to add it with the inverse of that alpha value. And that's how you kind of get blending working, and that's where you get the alpha blend. But for additive, you want to, instead of doing the inverse, you want it to do a solid. So basically, you're adding the source alpha to whatever the scene already existed. So if you reload, you'll get that exactly. So it'll look like a hologram. I'm going to touch this a little bit later. I just wanted you guys to know that it's here and how to get it to work. Don't worry too much about the math behind it. For now, I'm going to go that over on the next chapter, which is going to go over texture blending. Hope that's not too much math on there. It will really get a lot clearer once I have textures to show you guys. But I just wanted you guys to know how would you do an additive shader, and it's basically by doing this magical blend function. So now, if I just go over everything again, you have the opaque shader, alpha blend, alpha test, and additive. And the additive is going to be an X-ray. You can kind of change the color. It'll look a lot brighter and whitish than your other ones, just because of the nature of you're adding the color onto the scene. So most likely it's going to cap out. Hope you guys enjoyed this one. Next one is going to be about texture blending and getting pelletization and all that kind of good stuff working. Okay, so in this chapter, I'm going to show you guys how blending of two textures or two colors, it kind of works in HLSL and CGFX. And it'll basically teach you guys how to mix between two colors or use a texture to kind of blend between two textures. This can be used for pelletization, which means you have a black and white texture and you want to put a color in there. Or you want to have, say, like a car shader that has, you can pick multiple different colors using the same texture. And this is huge in games, especially in things like character create, to where the user can pick their own color and you kind of have to funnel it to the right places, as it were. And when you want to have one map kind of be able to change its color however it wants to. And so to do that, I made a new shader called blended.cgfx. And it's like the Phong, where it just has the color and the lighting information. I made it plain because it's going to be easier to see the texture and all the blending that's going to be going on, as opposed to a sphere. And so yeah, let's get started. Okay, so the first thing we want to do is we want to add a new map to our shader. That's going to be our blend map, which is going to blend between our shader color and then a new secondary color that we're going to add. And that's the most basic kind of blending, to where you have a black and white map, and black is one color, white is another color. This would mean that it would work if you have gradients going through black and white, but for the most part, you don't want color blending to work, because sometimes, especially if it's like character create, the user can pick two colors that don't go well together, and then you get some muddy color in the blend. So usually they're sharp maps, but it works either way. So the first thing we're going to do, let's open up that blended.cgfx, which is just that plain shader that has the Phong and everything we want. And let's add a new texture to it. So So it's the same way we've done the other textures. Let's do texture, blend texture. And then let's set our sampler. And if you have a shader open already, you can just kind of copy and paste and just typing it all out because I don't have anything handy. But you can most certainly just copy and paste from an existing shader you have. And let's just see if this compiled. Save. Oh, let's see what I messed up. Probably missed that semicolon right over here. Now, I also missed the guy right here. Okay, so now we compiled, and our texture is there. Close that back out. And it's usually good to kind of refresh fast because you will inevitably be making typos. And I do it all the time, so it's perfectly normal to forget a semicolon here or there. So then we want to, let's also add a second color. So I just copy and paste. So I'm going to choose shader color. Just call it blended color. And let's make our shader color default to red. And our other color default to blue, so we can tell the difference. And so I'm going to do the long way first, and then I'm going to do it the short way. And hopefully you guys understand the long way, and it'll help you clarify some of the stuff that I went over in the additive chapter, in the blend modes, and hopefully clarify a little bit of that. So first we'll make a new variable. Let's call it final color. And what we wanted to do, actually, yeah. And then we want to add a new float, which is going to be blend, and it's going to be the reading of our map. And we want it to be a single float because it's going to be a black and white map, and for our math purposes, we don't want it to be a colored map yet. Not in this type of blending. I'll show you in a little bit how to do a more complex blending to where the red channel is a color, the blue channel is a different color, and the green channel is a different color. But for now, let's stick with simple. So, and we want to just grab the red channel. Okay, so our final color is going to be, and so let's step through it. So the way the blending is going to work, let's just see the blend map. Let's multiply the shader color times the blend. Let's move this down here so we see what that will look like. And let's load in our, so you'll see that the blended color came in, it's defaulting to blue properly. Let's set the blend map. And I've added an image to our textures directory called AB blend. And it basically is a black and white image that it has A and B written on it. So you can kind of tell how the blending works. So pretty straightforward. We have the blend. So let's just see it by itself. So by itself is black and white. By multiplying it against the color, whatever is white is going to turn the color, and whatever is black is going to be 0. So the way it works is white is 1, black is 0. So if you multiply something by 1, you'll get the same thing. And if you multiply something by 0, you'll get 0. So by multiplying our color against the blend channel, or the blend map, you basically get color where it's white and then black where it's black. And now we want to add the second color. So the way we want to add the second color is we want to basically flip that mask. So now black is white and white is black. And we want to multiply by the second color. So let's do that just to see what that would look like. We want to do 1 minus blend to flip it. And let's do, what do we call it? Blend color? Blended color. Basically, we flip the image, black is white, white is black. So we can see that isolated real quick. So that works. And then we multiply our second color. So basically now you have the inverse. And since we're adding two things together and 0 is, like if you can add 0 all day long and you're not going to get anything, it's safe enough to add what we had before and what we have now. So basically the regular version of the map multiplied by one color and then the inverted, and it should basically match and fill each other up. So let's add shader color, multiply by blend, plus, let's put parentheses just to kind of show exactly what's going on here. And there we have it. So now it's properly blended between the two colors. You can pick your color here and go to town. And everything works as it should. So you can see how if you had a hat or something other in Character Create, you could basically make a black and white map and then you have two colors that the user can pick. And as well, so the way the additive work, basically that first parameter was your blend map, and then the second parameter was the inverse of the blend map. And it basically, the way the blending works, you have that function and it adds the two arguments that you passed. Let me see if I can fire that up. Let's open our techniques. So basically this blend function is you take two arguments. It's going to be the source alpha and then the inverse of the source alpha. So it's essentially the blend map and then the inverse of the blend map. And in this case, our blend map is the alpha. So I hope that makes perfect sense to everyone. And it basically add this plus this. But since we want it to be additive, we want to add 1 to the alpha. So it basically means 1 is essentially the scene. And then you're adding anything that's the alpha. So that's where the additive kind of comes from. All right, so hopefully that clears that chapter up. So now we have the perfect blending, but since that's a fairly common thing to be doing, CGFX and HLSL, they have a new function, which is not new, it's been there forever, but it's a function essentially made for that, which is called lerp, which is a linear interpolate. So you can pass it a shader color and then blended color. And then as a third argument is your map. Oh. And it should do everything for you. I passed in the wrong order. So let's flip it. And there you go. So it's essentially the same thing as before, but it's a lot shorter. And it's kind of pre-made for, you're always going to want to blend things together. It might not be colors, it can be normals, it can be vectors, it can be anything. So it's kind of a useful little helping tool. And next we're going to show how to take a texture that has red, green, and blue channel and then funnel a color into each of them. We won't be using lerp, we're going to be doing it the other way, but it should be really straightforward, and let's get cracking on that one. Okay, so to do a 3-color map, technically you could do a fourth one too if you want to use black, or you can even do 5 if you want to try to get into alpha, but for simplicity's sake, let's just do 3, red, green, and blue, and each of them replaces a color. and we want to add a third color. So it'd be call it third color. It's going to be green. And let's just call it third color for simplicity's sakes. And then we want to change our blend map to be a float 3 because it's going to have red, green, and blue channels. So we can change it to be RG and B. And our final color is going to be, so let's just start with blended color. Let's do first one, shader color times blend R. So what this does is it just isolates the red channel of that blend map and multiplies it against the shader color, so we can see what that would look like. Let's change our texture to this RGB blend, which is just a red, green, and blue. Really simple texture. We can isolate just the red color just so we see exactly what we're getting. But you can probably imagine what they'll look like. It's just a black and white of the red channel. So what I want to do is let's add this, and then we can just simply do our blended color times the blend blue plus our third color times blend G. So this is essentially the same as before, but since each map has its own, or each color has its own separate channel, we don't need to do any flipping. We needed to do the flipping of the inverting the black and white channel because we wanted to use black as a color, and right now we don't really care for black as a color. We could, and we could get a final color if in case it was purely black, but that's just asking for trouble usually. So let's see what that will look like. And hey, it looks like the red green, it looks just like the texture, but now I can go in and change the color however I want. And this is really useful, especially if you want like things like cars or buildings we've used, to where basically you have a brick texture and you can pick a different color for a brick. So you can have darker red and a lighter red, or you can have things like concrete with different shades, so you can show a difference. We've done cars as kind of the obvious one, but we've done pedestrians like clothes or even skin colors and hair. It's kind of, sky's the limit, and it's really, really useful to, so instead of having a texture that's, if a guy has white hair or if a guy has black hair, you just have one texture and we can just palletize it in the shader and save a ton of instructions and a ton of memory. Hope that's been helpful. Hopefully I clarify some of it. It's really straightforward technique, but it goes a really, really long way in saving memory. Hey everyone, in this chapter I'm going to show you guys some more practical techniques. In this particular chapter I'm going to show you guys how to take a generic cubemap shader that we have already and turn it into a nice slick car shader. This doesn't look bad, but it could look a lot better. So I'm going to show some little tips and tricks to kind of how to take it to the next level. And I basically just made a new shader and applied this car shader, CGFX, which is the same as what we had before at the end of the cubemap chapter. So it's the basic Phong with the cubemap texture. And instead of using that Uffizi probe, I'm using a Sky Dome cubemap. You kind of get some clouds and you can get a little bit of sun here and there. You can kind of see just a little hint on the corners. So what we want to do is first we want to play with the Fresnel a little bit. So the way we have it, we only have Fresnel power as a control, which is good, but we kind of want more control. We want to be able to crank the intensity on the edges. We want to be able to control the cube map a little bit, and I'm going to show you a cool tip to kind of kick it up a notch. And then there's also, I'm going to show you how to do an offset on the cube map, to kind of, or on the Fresnel, so you guys have an even coating on the car. And then I'm going to show you how to change, how to make a double specular to where this would actually start looking like the reflection of the sun on the car and how it scatters with the paint. And This is just a really basic car shader. It doesn't have any textures besides the cube map, so you could go crazy and you could make a really nice paint fleck, normal map, and all sorts of crazy stuff, but I want to show you just how far we can take it with just plain shaders and just a single cube map texture. Okay, so the first thing we want to do is we want to open up our car shader. And you'll see that it's pretty much the same as the cube map shader that we have, where we have the Fresnel. I added ambient color to the masking of the Fresnel just so we can get Fresnel all over the car. But pretty much the same thing. We only have the one texture, the one reflection texture. So first thing we want to do is we want to add some more controls. The two things that come to mind out of the bat is Fresnel intensity and Fresnel offset, and I'll show you guys what the Fresnel offset means. 0. And so as you can imagine, the Fresnel intensity is basically going to multiply against the whole thing, so we can up the brightness a little bit. It's essentially a reflection intensity, you could call it that too. And then the offset is, since we have Fresnel just on the edges, we want it to be really high in the edges, but we still want to have a little bit all over the car just to kind of show that it's still very, very reflective, and it kind of gives that clear coat look. So let's actually implement them. So let's go down to where we're making our Fresnel, and we'll want to multiply everything by the intensity plus Fresnel. Let's see how that looks. Come in here, reload. All the way down. So the intensity is behaving as we want, and then the offset is also behaving. So if you see, I can crank this all the way to the edge, and the intensity is kind of gonna just, you're still gonna have the black spots in the middle, but with the offset, it starts to fill in. So the offset, we want just a hint, just so you can see some reflection. Intensity, we probably want around 3. And this little garbled is aliasing, and I'll show you guys in a little bit how to minimize them. And then the power, we can kind of keep it around 7-ish. Starting to look a little bit better, not too much, but at least like the side is starting to look a lot more defined. Try to up this a little bit. Too much. And a lot of this is going to be personal taste and artistic taste. So like that starts looking nice. Getting the glancing angles. So here's the real secret. The real cool thing and the real trick is to basically you need to amp the contrast on the cube map, and this will make a huge difference. So to do that, we will want to make a new variable called contrast. Want it to be at 1. And to basically to increase contrast, we'll do the power function, the same power function we're doing here, but we're gonna do it on the cube map, and you'll see in a second what that does. It will basically shove the dark colors down and then bring the bright colors up as contrast would. Well, what that gives us is we can start pushing that intensity a lot more, and you start getting some strong defined look. That might be even a little bit too much. Maybe bring the intensity down. That's where you start playing with it. Kind of get the look you want. That contrast might be a little too hot. But you can kind of see that this is what your cubemap kind of looks like. Kind of washy and not all that appealing, but once you crank it up, it'll start to push the darks and it'll start popping the colors out. I've done this technique when I was doing rings in a game and kind of jewels, and it really helps. And it gives the artist the control to get exactly what kind of reflection. And if you look at different metals will kind of basically amp the contrast of the reflection, and some will have like really rich dark reflections, and the other materials, like cheaper materials, will kind of have a little film over it. So that kind of helps the artist give exactly the look they want. So cool. So the next thing is you can kind of start seeing that could be at some point a sun. So if we crank that specular contrast power up, so we got a really sharp highlight there that starts looking like the sun, but usually the sun in the sky brightens the area around it. So what we're going to do here is we'll want to add a second specular. And the way to do that is we'll come back to the shader and basically be duplicating this whole thing. But since this is kind of expensive, it's not really expensive, but we don't want to be doing this multiple times, and this is going to be the same exact thing in both specularities. Essentially what we're going to do is we're going to do this. We're going to take this, we're going to copy it, and we're going to add it to itself. But we want to, of course, we want to control it a little bit differently. So we'll make two new variables up here, which is specular power 2 and specular color 2. Back down. Change the specular power to be specular power 2 and specular color 2. And just for cleanliness sake, make a new variable. Call r.l, which is reflection.light. And that, paste it there. That's just to kind of keep this line under control, because otherwise it's way too big. So just to recap, we had our regular specularity here. We just want to add the same specularity again, but we want to control it differently. So basically we're going to give it a bluish color and a little more white fall off. So just see it in a second. There it is. So we'll want to kick the light back a bit. Maybe give it a bluish kind of tint. Don't want to crank it, the tightness. But you see how, so if we turn this off, you just have that little dot, which doesn't look like the sun at all. But if we kind of add that second, it starts to look like it's the sky. So let's take a look at these jaggies. These jaggies are basically aliasing. It's a common rendering problem, and with Maya 2012, they added the viewport 2.0 stuff that you can basically enable anti-aliasing in the viewport itself, which is actually pretty nice. So what we want to do is we want to turn it on so you can see viewport 2.0, and then you want to click the option box, and then in the option box, go to multi-sample anti-alias, enable it. You'll see that it starts looking better. Just crank it all the way up. So you can see it's still there, but it's not nearly as bad. And the viewport 2.0 has some nice features. You can get you select your camera, you can enable depth of field in the viewport, which starts struggling a little bit, but it's pretty cool. You can kind of up far, too far, 10. These variables. And there's motion blurs and also sort of other viewport niceness things. And it supposedly it pushes a lot more poly, so if you kind of have a heavy scene going, it's definitely worth the investment for the new My version. So there you have it. That's pretty much the car shader. But now so we still have all these other parts that could use some shading. Let's see if we can use the same shader to get a metal look on these rims. So we'll just duplicate our shader in the hypershade. Go duplicate, then assign it to that model. We'll want to assign that same cube map that we had it. Of course, we don't want the wheels to be black. Some cars have it, but won't. Bring it up. Starts getting metally, but still not there. Assign the light. We can start playing with that contrast. We can get that cube map to show. Get contrast as well. So now you can start getting some metal. Kind of tweak your heart content. Another good way of kind of checking out if your materials are good, just make a sphere right next to your model. Assign another sphere. Assign our car. So you can kind of see what your material really looks like on a sphere. Sometimes the model will throw you off and you have some curves and you don't know if the specular is in the right place, but with the sphere, it kind of clarifies everything. So hopefully this was helpful. Just a couple of little tricks along the way. The main thing to take away is the viewport 2.0, so we can kind of not have that nasty looking aliasing. And then the contrast, how to contrast textures. The cube map is the one that really benefits from having contrast. And then just the extra controls that you're going to find yourself needing or your artists are going to ask. And the more control you give an artist, the better iteration they can, or the faster they can iterate and the better your end product is going to end up looking. So finally, we can start trying to change colors. Cars are tricky to get it right. And a lot of the properties might change, like reflectivity based on the color. Black is kind of the easiest to make look good. White is freaking insanely hard because you're basically blowing out the whole time. So you can kind of have to make it look gray, but then you kind of have to shift it. That's hard. There it starts looking. Then you kind of have to play with the reflectivity. Red is basically kind of have to drop it down half intensity so you get the full range. And if you're going to do something with textures, one of the cool things to do is to, in the spec, on the second spec, not the sun spec, you kind of have a texture that's just noise. And it'll look like there's paint specks on the car. Kind of looks nice, but not a bad simple shader. So, kind of see what it looks like on a sphere. Yeah, so next we're going to do a character. I'm going to show some more tricks on. I'm going to try to do some crazy stuff like subsurface scattering. We're going to try to do some more fancy ambient models. And that's it. Hope you guys are enjoying it. And by now you should pretty much have a really good idea of everything that's going on. If not, just kind of take your time. I know that I kind of blow through a lot of these things, but the idea is that you'll pause it, kind of try to do it on yourself, by yourself, and just kind of keep at it, and you guys will get it. It's really straightforward once you kind of figure everything out. Okay, for this chapter we got E3D's awesome little vampire guy, and I've set up an Uber shader, which is essentially just what we had before with the Phong, with the cubemap added, which is just the normal specular and diffuse textures as well as a reflection map, and I apply it to this guy. Let's open it up. So the only kind of difference that you should note is I've added this inverting of the world by normal, and this one I should have said before, but depending on your engine and depending on how your artists are authoring your normal maps, there's you probably heard like the flipping the Y. Sometimes the engine will do it for you, sometimes you have to do it. Maya wants the Y flipped. It's usually an option when you're baking your normal maps, but these normal maps were baked with it flipped, so I just had to add that negative in there. But besides that, everything is the same as you've seen before, and we'll kind of get cranking on it. The first thing we want to do is we want a more robust ambient light, because right now it's just kind of a flat color, and this guy is looking kind of sad. There's no life on him. It looks nice because the model is really nice, but it's kind of deadish looking, so we want to pump it up. And we want to do the same thing that we did with our reflection on the car shader. Kind of pump it up a notch on this. So the way we're going to do ambient is, if you heard of spherical harmonics, it's a very, very, very simplified version of it. It's essentially like spherical harmonics, the first degree. And all we're going to do is we're going to add essentially what Unreal calls a skylight, which is you have a top color and you have a bottom color. And I'll draw it out for you guys real quick. Alright, so if we have a sphere, and basically, usually the Lambert, the way it works is if you have a light coming down, you're going to cut it down the middle, and then you're going to have, this is going to be 1, this is going to be 0, and this is going to be a -1, right? So if we have, this is your light, and then you have your normals kind of pointing these ways. So the way we're going to do this is we're going to do a color on the top and a color on the bottom. And we're going to basically blend it between a hard-coded light. So we're going to make a new light, fake light, that's just going to be an up vector, and we're going to basically get a color coming from the top and a color coming from the bottom. Because this is going to be, if you remember the lerping chapter, this is going to be 1, this is going to be 0, this is going to be 0. So basically, it will blend between the top color and the bottom color for us. So let's actually implement it. So first thing we want to do is we want to hijack the ambient color. We want to call this top. Then we got to make a new one called bottom. And for now, let's default it to 0. So let's come down here, make a new variable called ambient color, just so we can hijack already here where it comes in. We don't have to worry about it. And it's going to be a lerp between bottom color and top color. And here's the trick. So essentially going to be this guy. Copy and paste him here. But instead of the light direction, we're going to hard code a nup vector here. And let's see what that looks like. So as you can see, it's just as you expect. He's being lit from the top from an invisible hard-coded light. And we can kind of control. Usually you want to give it kind of sky color. And then from the bottom, you can leave it black, but we want to give it a little light. So a little bit. You don't want the ambient to be too ambient, otherwise it kind of defeats the purpose. Kind of bring it down, but you can see it will give a lot more definition, especially with these nice normal maps, than just kind of like a flat color slapped across the whole thing. And I've used these in multiple games. All right, so we reload. Now you can start seeing that there's a little more life in there. You can see a little bit of blue. There's a little more definition on that, on these areas. Starting to look a little better. Not there yet. So the other thing we want to do is we want to add a subsurface scattering to kind of add some life to this guy, because he's a dead vampire, but still needs to have some blood flowing underneath him. So to do that, bring your visual aid one more time. So just the same way that we just did, we have a light coming in from here. This is going to be 0, it's going to be 1, it's going to be -1. If we can, like, if you remember, we'll saturate this so this becomes 0. And then this is just going to be flat if you add anything to it. If we do add some stuff, if we add like a color before we flatten it, it'll basically bleed through, because this is not going to be 0. So if this was 0 and then we added 0.1, the whole thing here would become 0.1, as opposed to just a little bit becoming 0.1 and this still kind of become this remaining black. Hopefully that makes sense. I even made a drawing for it. So essentially is, do it again. You have 1, 0, -1. If you add 0.1, this becomes 1.1, and this becomes 0.9. But here, you're still going to get all the gradation between 0.1 to 0.9. And if this was 1, 0, 0, then this would be 0.1, and then this would also be 0.1, and everything in the middle would also be 0.1. So here we'll still get the gradation. So if we wanted to add stuff, it'll bleed through, as opposed to here to where it'll just look flat. So see what that'll look like in practice. So let's add a subsurface color. And we can stuff it in here. Let's make it just a little bit of red. And just for testing sakes, we'll add it before we get to saturate. Let's see what it looks like. And then we'll add it after the saturate so we can see the difference. So what you see, that's what we had before. Too much. 0.1. That's what we're getting now. Let's switch back and see what it will look like if I added this after the saturate. It basically kind of flood it so the whole thing would have that color. So we can make it more visible here. So as you can see, there's no black anymore. It's just washed out. That's what the drawing kind of is trying to say. But if we move it back inside before the saturate, you'll still get that nice subsurface look. And then you can still saturate it after, so the rest of your math works. But if you want to try to get that subsurfacey, and this is dirt cheap, one instruction kind of subsurface scattering. There's way more complex ways, but this is just enough to kind of give it. And sometimes you want to make a map so your paints don't have subsurface scattering, but for this example, we're kind of okay. Then the other thing we want to do is we want to play with that roll off a little bit. So what I want to add is I want to add a subsurface scatter. Let's go ahead and add that. So we'll want it to be a float because there's just a single. How many floats? Yeah. Paste. Call it subsurface spread. And it is gonna be do it from 0 to 1. Get to go to 0. And our default is 0. This part, it gets a little tricky. So essentially what we want to do is we'll want to multiply it by 0.5 and then add 0.5. So let's just see what that will look like. So we still have Lambert there. So if we multiply by 0.5, then add 0.5, you can see the spread is way more spreaded. So what we're doing is we're bring that back in. So if this is 1, 0, -1, now we kind of squished everything down, so this is half. This is still 0, and this is -half. And then if we add half again, come on, Photoshop. This will pop back to 1. This will go to 0.5, and this will go to 0. So essentially what we did is we shifted everything up 0.5, but without kind of blowing out R1. So let's do that again. So by default, doing a Lambert, can't do a circle today. This is going to be 1. This is going to be 0. It's going to be -1. What we want is, we don't want this to be 0. We want 0 to be down here, or maybe down here. Basically, we want to pull this way. So to do that, is we want this line to actually be 0.5, but we still want this to be 1. We don't want it to blow out. And we want this to maybe go to 0, or close to it. If it's still negative, we'll clamp it to 0. So the way that we solved that was, so at first we have -1, 0. We scale it. Now we have 0.5, 0 still, and -0.5. And then we added 0.5 to it. So let's do times 0.5. And then we did plus 0.5. So now this is 1 again, but this is 0.5, and this is 0. So what this would mean that this is black, this would be 50% gray, as opposed to this being full black. So it kind of softens it up again and basically is spreading it out. Hopefully that math makes sense. If not, you will see it live in just a second. And the other thing that we'll want to do is, so this 0.5 and this 0.5, they're basically inverse of each other. So if this is x, this is 1 minus x. So 0.5 is just perfectly down the middle, but if we wanted to pull this by 0.2, we would have to do this. We'll multiply it by 0.8, and then we'll add 0.2. And that's just so the math works. Don't worry too much if I lost you there. Just know the formula. You'll be all right. So as you can see, 1 is still 1. What used to be 0 is now half, and what it used to be -1 is 0. Essentially, what was white is still white. What was black is now gray, and what was really black is black. So what we want to do is we actually want to use that variable that we made. That I even forgot how we called it. And we call it subsurface spread. 1 minus subsurface spread plus subsurface spread. Because this is all happening before that subsurface color comes in. Try that one more time. There it goes. Okay, so now our spread is 0, so there's nothing more besides just what we had before. So the subsurface is still there, but it's not getting pulled. So as we start adding, you can kind of see it roll off a little bit. So at 1, everything is 1. So essentially we pulled it all the way across. But at half, still kind of bright, but we still have some points of black where it's perfectly behind the light. So I probably want like a 0.2 somewhere in there to where still there's some nice fall off, but it's not too ambient looking. So hopefully that makes sense. We're basically letting the light wrap around a little bit to create a sphere. That's what it looks like on it. Stereo. So if we're behind, you can see it kind of bleed through. That's essentially what subsurface scattering does. It kind of pulls the light around. So here it hasn't blown out because we're doing that scaling trick. So our 1 is still 1, but we let that light kind of come around and bend and scatter. So if the scatter is really high, it just goes all the way through. But if it's half and 3/4, you start getting some nice reds, even if you're behind the light. Just kind of what you want. Does that make sense? Let's come back and re-enable everything so we can tweak it a little bit. Alright, so now he has a little red on him. Kinda. This is really a personal choice. You can make him have a green undertone. If you want, you can make him have blue. Even looks colder. I personally like warmer colors, even if it's a deadish vampire creature. Sometimes if you're gonna do like a nice creature or something like that, you probably want to give it a blue subsurface, but if it has life there, it's kind of nice to give it a warm color kind of going through. And kind of take the spread. There's some fall off and it starts looking more alive. So finally, the last thing we kind of want to do is tweak this a little bit. You can really see how that scatter looks like the light's kind of bleeding through. The last thing we want to do is we want to fix this reflection map. We want to do the same trick we did with the car, which is that reflection intensity and reflection contrast. So let's add that in. So we're going to add two variables. Intensity default should be 1. And the default should be 1. Max should be higher than that, and the intensity should also be able to go higher. Alright, so here where we read the cube map, we'll want to do a power with the reflection contrast. And we'll want to multiply it by the reflection intensity. So exactly like we did with the car. So basically the reflection intensity will multiply this whole thing so we can get brighter reflection, and then the contrast is going to do a power. So you're basically raising that texture to the power of contrast, and that's what it does. Let's reload. Nothing should change. We start cranking the contrast, and you can see that he's reflective too, so there's going to be some work there, just because our reflection mask is not very tweaked. But you can see that this starts looking better. Then as we amp that contrast, so like I said, he's still pretty oily, so we'll have to kind of just play with our maps a little bit. But it's the metal starts looking a lot better. And if you wanted to get that anti-aliasing, you can do that here too. Kind of help solve some of this. So a lot of that goes away, a lot of that noise. And then it's just a tweak fest. And there's people that can sit here and just tweak all day. And I'm one of those people. So at some point, you just kind of say, all right, that looks good enough, ship it. And you have to go back into your textures and kind of take in consideration the new cube map stuff, but for our sakes, it looks a lot nicer than you did before. And it's a really nice model, and it's a really nice game. Game Res, you guys should definitely check those DVDs out as well. But now you can see that that doesn't look milky anymore. It starts looking like metal. That's what we try to do here. Try to make it look as good as possible. Hopefully you guys had fun. Hopefully you guys learned a lot. This is just about all of my tricks and tips. And feel free to email me with any questions or comments. I'm sure there are plenty out there. Hopefully you guys enjoyed it. Hopefully it was informative. And next chapter, I'm going to go into Unreal and show with the shader network some of the stuff we did. So just like some basic Lambert and some dot products, and play around in there a little bit, just so you guys can visualize with the nodes what we did with code. But if you made it this far, congratulations. You are now qualified to write shaders professionally, and I will vouch for you if you understand everything that I said here. All right. Hope you guys had fun, and see you in the next chapter. Okay, so in this chapter, we're inside the UDK. As you can see, this is a new material from scratch. I just right-clicked in the content browser and made a new material. And what we're going to do here is we're trying to recreate that first Phong that we did with all the lighting inside of Unreal, just so you guys have an idea of the steps we went through and how to do it in Unreal, and also kind of how to visualize the whole flow of the shader with Unreal's materials. So one of the things to note is under material here, the blend mode. These are the ones that are part of the technique. So we have opaque, masked, and masked is the alpha test. Translucent is the alpha blend. additive is the one we did, and then these extra ones we didn't go through, but modulate's essentially, instead of it adding things together, you're multiplying, and then these other two are some extra Unreal special ones. So let's go ahead and just keep this as opaque. And lighting model, Unreal has these basically plugs that you can use if you want to just kind of leverage the math. You don't really have to worry too much, and it will do the Phong inside. But for our sakes, let's change it to custom, and basically it will ignore all of Unreal lighting except the self-shadowing. But anything that will plug into this custom lighting plug, then that's essentially going straight out to the shader. So first thing we want to do as a test is we want to add a vector parameter. And vector parameters are essentially variables that the user can change, which are the ones that we used to write on the top of the shader. Constant vectors are just essentially if you hard-coded like the up vector in the ambient color, we can do it that way. But let's name this shader color. And let's default it to red. So if you remember, you can probably start seeing it in your head what the code for this would look like. It would be like float 3. This is actually a float 4. Shader color, default, red. And then we pipe that into custom lighting. And there we have it. And they have this, it's really just self-shadowing. Your shader is still just a constant, but there's that self-shadowing. If you hold down L, you're controlling the light. I kind of wish Unreal didn't have this, and maybe there's a setting somewhere to disable it, but I don't know where it is. But this is the most basic shader, so this is that super simple that we started with. It's essentially the shader color getting shoved straight through. You don't have access to the vertex shader. They've added some stuff to like with this world position offset that lets you at least play with the position and do some of the vertex animation stuff that I showed you how to do. But you don't really have to worry about UVs being sent through or any of the other kind of under the hood stuff. So next thing we want to do is we want to add a normal, and we're going to go straight and add normal maps because there's not a good way that I know of to use geometry normals. There's some hackery that you can kind of do with a combination of nodes, but I'd rather just go straight into the normal mapped. So let's do texture sample parameter normal. And this basically does all the multiply it by -1 and or multiply it by 2 and then take 1 out for us. And in the content browser, I just did a search for tile. I'm going to get that guy. And if you have something selected in the content browser, you can just hit the arrow and it will hook it up, and you can see the color changed because they're doing that compression trick. And the next thing we want to do is we want to do a vector transform, which was that part that we multiply it by the matrices. And basically what this is going to do is the original texture is in a tangent space. I want it to be in world space. So if we pipe that out, it looks a little bit different than what we had because Unreal changes, they have Z up as opposed to Y up. So in Maya, we used to have the side was blue and the top was green, but it's still the same kind of principle. So blue's on the top, white's on this side, and then red's on that side. So still relevant. What we learned in Maya is just a little bit different, but it should still make sense. So now we have our normals, and you can see this is a lot faster than writing it out, but once you start getting into more complicated stuff, writing shader, personally it's faster for me. For some people, doing the nodes in Unreal is faster, but depending on your engine, you may or may not have a fancy shader editor. So let's get in a hard-coded float 3 just to do our kind of light. And we can do a constant vector 3. And we want it to be Y is up. So Z is up in Unreal. And we want to do our dot product. So all those guys are still here. And they still should make sense. So that is our this light is misleading, but it's just a self-shadowing. So what we have here is a top-down dot between an up vector and the normals, which we've done before. If we wanted to do it, we could use it to lerp a top color and a bottom color, or we can change this around. And you see, because we didn't normalize this guy, stuff's starting to blow out. So from forward, if we wanted to normalize, all we do is add that node and plug this vector in, and then that guy out. So basically what this means is this vector is going to be normalized, and then the output, which is the normalized vector, is going to go into one of the two slots on the dot. Hopefully makes sense. Let me draw it out. So before we had that, so we had dot, and then world normal, and then the light. And writing on red on top of red is not a good idea, but you guys get the idea. So what this is this dot, and then the world normal is that guy, and then the light is this guy. So back in here, hopefully that makes sense, but the hard-coded light, it's not that great, so let's actually pull in the light vector. And let's just shove straight across and hope that Unreal normalizes their stuff before sending it across. So there we basically have our basic Lambert that we started off way in chapter 1 or 2. We can use the little skull to clean out things we don't use, but it killed things that we did want to use because we still want that shader color. So let's just delete these guys out. So I don't know if you guys know about how to use this editor. Control clicking selects multiple things. Hold down control and you move it around. If you just click and drag, you'll move the camera around. The wheel zooms in and out. So I'm going to start cleaning this up. And I've seen shaders that are pretty gnarly to where you have to be zoomed out to see the whole thing. And we'll get there. It's a matter of time. So here we have that guy multiplying everything pretty, or the dot product. The next thing we want to do is we want to do the saturate, but Unreal doesn't have all the functions that we wish it had. So they do have a constant clamp, which will clamp it between 0 to 1. You can change that to be different values. So let's use that instead. And what that's going to do is that's just going to make it so that guy is 0. So when we add our ambient color, it's not subsurface scattering, it's pure ambient. But first, let's add a multiply. And we basically want to multiply all this guy with that shader color. And you get what you expect. So if we duplicate this with Control W, we can change this to be ambient color. And I want it to be default 0.1.1 all across. And let's add the dot. So let me see if I remember how to make comments. I'll be able to press C. Guess not. And do new comment. And then a pop-up is going to pop up as it would, and we can call it Lambert. So then you can click and just grab all of Lambert. This guy kind of got stuck. So now we can kind of remember this whole chunk is our Lambert coefficient or diffuse or n.l, however you want to call it. And we want to add our ambient color to it. And at any point, you can kind of just hijack that output so you can see what that was going to look like. Again, that ugly self-shadowing is over there, but try to ignore it. So that exhibits what we want, and we'll multiply this new output with the color to give us what we think it would give us. Let's try to move this out of the way a little bit. So now let's set a texture. So textures are super simple in here. Texture parameters 2D. So if you remember, this is our sampler 2D, this is our sampler cube. Because I have this selected in the content browser, it automatically assigned it, but I want to assign the diffuse variation of it. We can just multiply it straight, and we have what you expect. We can also multiply the shader color with the diffuse or with the diffuse texture, which get the multiplication. But this will give you some basic tinting of that texture. So let's start moving this back out. So at this point we have our Lambert with diffuse textures and normal mapped. Now let's add the Phong in there. First let's add Fresnel. So Fresnel, if you remember, is the eye vector, which Unreal calls camera vector. And it's the dot between camera vector, which we also are going to have to put into world space. Just make sure that is not right. So that started looking right. So I'm looking straight down Z. This still is kind of funky. Let's see if. Yeah, this camera guy is a little wonky. Let me try to see what is the proper setting. There it goes. So I'm looking down X, mostly red. Looking down Z, mostly blue. And I'm looking down Y, it's mostly green. That's good enough. So basically, this guy's coming in tangent space, and we got to shove it into world space, just like the normal maps. Okay, so now we want to do a dot product between our transformed normal map and our eye vector or camera vector. And that gives us what we expect. So we want to do a 1 minus to flip it. Which gives us that. So still makes sense. We have dot between normal and eye vector. And then this is 1 minus to flip it. And now we want to add a power to make it tighter. Power, and then we can do what Unreal calls a scalar parameter, which is essentially a float 1 parameter. And we'll call this power. Boom. That's not a good default. Good default is 3. So as you can see, 0 is pretty busted. 1 is what we have by default. 2 starts to grow. 3, 5. And you start getting some bloom too if you start to blow out. It's one of the nice things about Unreal. Kind of the post processes that are built in there. So we got that guy there. Looks good. Make sure this dot product is saturated before that. So we can either duplicate it here. Just so when we start adding it together, it doesn't look nasty. So as you start doing more and more shaders, you're going to start kind of running that way. So you Control A, make a marquee selection, and then Control drag, kind of pull them back. You can make a new comment here. And this is Fresnel. Technically, Unreal also has a Fresnel node that does this whole chunk for you, but we're learning, so we want to do it ourselves. And what we'll want to do is we'll want to add the Fresnel after you've multiplied the textures together with the Lambert lighting. So that gives us what we expect. It's a little bright, so let's add another scalar parameter called Fresnel intensity. Default to 2.5 and multiply it. So we're multiplying Fresnel by the Fresnel intensity, just to kind of bring it back down a little bit. Cool, so we could also multiply it by the diffuse if we wanted to kind of kill some of this stuff. So let's go ahead and do that just for experimentation. And Unreal is nice to kind of just throw this stuff around to where you can really easily see all your changes. So you can see I knocked it down a bit, but you still have it right here. Crank it back up with some. Now finally, let's add the Phong in. So let's move this guy back out. You can see how it can easily become a spaghetti string mess. That's why these comments are really helpful. So if someone opens, they can kind of see at a glance, okay, this chunk is doing this chunk is doing that, this chunk is the texture, and you start kind of just learning the way to land. Then, so for the Phong, unfortunately, Unreal doesn't have the reflect function, but it does give us a reflection vector. It doesn't have the normal map, which kind of sucks, but kind of roll with it for what we have. So if you remember, it's going to be just like the Fresnel, but it's going to be a dot between the light vector and the reflection vector. So let's do that. Let's see what that looks like. Boom. Okay, so that's almost right. Probably needs to be put in the right space, because it probably also comes. There it is. So now, ooh, it's even worse. Huh. Okay. Starts looking a little bit better. Light around. Okay. That is the beauty of Unreal. It's kind of hard to know what space everything comes in, but that's why usually you won't have to do this level of handcrafted shaders. Usually you can just use theirs because they're just doing the same thing. But just for our learning purposes, you guys want to see kind of how your math works. So here you got the camera vector, dotting with the normal, getting saturated, doing a 1- power. That's where it starts. So it's like, you could do this in one line in about 5 seconds if you're just writing out the code. But here it starts taking a little bit longer. But you don't have to learn how to code. So you get the good and bad. Let's do a power. Because if you remember, we got to pull in that tightness. And same way of the dot. This is, you got bow, and then you have one thing and then the other thing. So in our case, this is going to be a scalar, going to be the power, which is this exponent. And then this is going to be our dot of the reflection and the light. That kind of goes in here. That is make a scalar parameter. Let's name it spec power. Default it to 30. What that looks like. There, so that starts looking. So because we didn't saturate this dot, I'm pretty sure that's what's going on there. Do a constant clamp. There it goes. So basically there's -1. We were doing a power -1 to kind of bring it back into positive land. So that's something to keep in mind, and something that it's a lot easier to see in code, and you kind of forget to kind of throw these constant clamps all around. Let's grab all these guys and move them down a little bit, because you start getting these wires crossing, which is not fun. So what we want to do is we'll want to add our spec. But this is the Fresnel. We'll want it to add it to add those two together. Come on, these little nubs get hard. Then we'll add this whole thing with our diffuse. And then pipe this back out. There you have it. What's happening here is we have our Fresnel. We're multiplying it by our diffuse to mask it out. So this whole thing gets added to our specular. And then that all gets added to this other multiplication chunk, which is this is our texture, multiplying by the shader color. This gets multiplied by the lighting, and then it gets added to our spec. So hopefully makes it a little bit easier to see. You can do a spec map in there too to kind of make this look a little bit better. But for our purposes, this is how you do a Phong shader in Unreal. And as you start doing more stuff, you will get faster and faster, and you start being able to see the patterns. It can get really, really confusing, but you can always follow the little lines. But once you start doing kind of stuff to where you use the same chunk of code twice, towards like you're using this Lambert, plus you're using multiply it here and use it here, but then you're pulling everything back together. It's a lot easier to see it in code personally for me than with the visual graphs. But it's a fun tool, and you can see that you have almost all the flexibility with the plain code as you would do here. And there's also a custom code or custom node that you could write just straight up HLSL. So technically you can just write HLSL here and go, but I never really had to use it. We always made everything with just the nodes. Hopefully that's helpful. To add a spec map, you can just get a new texture, simple parameter 2D, and I'm pulling the spec map for that tile. And let's see, bring it down here, just multiply the red. Add it to the Fresnel, and there you have it. Starts looking a little bit better. And you can also make notes here. So this, you can say it's Fresnel plus spec, and this will help people. So this, you can say it's the spec times spec texture. Texture, not spec texture. So this should help people that come after you decipher. We've written some nasty nodes, but that's the way of the game when you're starting to play with spaghetti string that is the Unreal Material Editor. But it's really, really powerful, and it's a great learning tool. If you're just trying to test stuff out, you can kind of come in here, and there's a couple of commercial softwares that also do kind of the same thing. I've just gotten used to writing it, but if you want to kind of see it visually, what the code is doing, you can kind of do it this way. So this is our Lambert normal.light, getting saturated, add it to an ambient color. See if I have a shader up that I can. That is our Uber shader from the last chapter. So the Fresnel, right here, this whole chunk is right here. So let me bring that back up. Gotta make it smaller. So I vector is a scalar vector dot with the world normal. Then we're saturating. So that's the saturating. Then we got the 1 minus. And then this whole thing is getting a power with the Fresnel power. And then it's getting multiplied by Fresnel intensity, which we added. That's not on the shader. But it gets multiplied by ambient color. Maybe I didn't do ambient color on this one, but you could. But you multiply it by the Lambert, which is this guy. If you wanted to see what Lambert is dot, light, and normal. And this, we added the subsurface stuff that if you wanted to add, it would be right here. And you saturate it back out. So hopefully that all makes sense. And yeah, I hope you guys liked it. This should be a good fundamentals. You should, if you understand everything, and go over all the chapters, try to write it by yourself, kind of peek and cheat once you have questions. And then the real secret is to just do it, and do it a lot. You have to just pick an object that you want to write a shader for and just start doing it. And the more you have solid examples of things you want to do, the better you'll get. And then you start getting into water shaders, and you start getting into more complicated things. Hair, and that you can just look online, see what other people have done, and then try to figure out what makes theirs special and what kind of code they have to kind of make the look that you're trying to get, and then just go ahead and try to use it and try to implement it. If they put it up online, hopefully they're okay with you seeing what they did and also doing it. And yeah, just remember to have fun. I know it can be confusing and frustrating, especially when it's not going your way, but you can really, really do a lot of cool stuff. Shader writing is a very, very on-demand career. Artists are more and more starting to become shader writers. It's usually been required or just reserved for engineers, but people are starting to realize that sometimes an artist or a technical artist has a better eye to write some of these more specific shaders than an engineer would. No offense to engineers, but sometimes you kind of need an artist to do that job. And yeah, I've been doing shader writing for about 5-6 years now, and every single place I've gone, there's been a need, and there's always going to be, I think, especially as we go further into next gen or current gen and going into next gen, shaders are just going to be a giant part of production, and that's where a lot of the art is really going to be pushing the limits of what we can do. So hopefully this was informational. You guys enjoyed it, and feel free to email me with any questions.